Yes, I'm still here. What do you prefer I do? It doesn't matter to me. Is it easier or harder for you one way or the other? Okay, I can do that. Great. Oh, wonderful. AJ just joined. Thank you.
Hey
Hello.
there.
Did you get your stuff working?
No, I didn't. So suppose I have 10 minutes of pre-recorded video before this is a wash. Oh, Stuart, FYI, I'm talking to Kalina on the horn.
As another option, I can try to run it on my
Hi everyone,
computer,
thanks for
but,
joining us in this virtual tutorial. We're excited to share some
probably have to
techniques
talk
that are
over and tell me what to
underrepresented in the
do.
visualization community, specifically using
might
cinema
work.
software tools for visualization.
Um,
My name is AJ Christensen, and my co-presenter Kalina
yeah,
Borkiewicz
I
and
guess
are part of the Advanced Visualization Lab at
my
the National Center for
recommendation
Supercomputing Applications.
would be
Before we get started, I
that
want to
if
get
we
everyone up and
do
running with our
that,
tutorial notes.
that
So if you haven't downloaded the Houdini software yet, you can do that here at this link. You have to go to the URL, tinyurl.com/IEEE-VIS-Houdini. And if you haven't installed Houdini yet, you can do that through this link here at the top, which will take you to this website where you can click Download Free Houdini Apprentice. It's a bit of a big download, so please start that as soon as possible so that you can keep up with the rest of the tutorial. And then please download this zip file, IEEE-VIS-Houdini.zip, just by right-clicking and saying Save Link As. And that should bring up a download dialog here, and you should just save it to somewhere that you will recognize, because later we'll need to be able to refer to the folder that it's in. And then finally, we've created a Discord channel or server for this tutorial. So in order to get on that Discord, you just click the link and then say accept invite, and you will bounce to a couple different sites, and it will eventually take you to the Discord server. And you will see in the Discord server that there is a general chat channel, and this is just for everyone who's participating in the tutorial today to converse with each other, share an introduction to yourself, share any interesting things you're discovering, or ask your fellow course or your fellow tutorial attendees for help. The Houdini questions channel is specifically the one that Kalina and I will be monitoring and trying to answer technical questions during. Please, please, please share a screenshot of any technical issue you're having so that we can quickly figure out what's going on and try to help you. And actually, a colleague of ours, Stuart Levy, may pop in and help. So if you see the name Stuart, that's who that is. Stuart is here to help as well. And then finally, this tutorial tips channel is just sort of a preemptive FAQ. This just has some useful tips for Houdini answering questions that we've gotten a lot in the past. So, I think that covers all of those resources. So, why should you listen to us? Kalina and I have a combined 17 years working in the field of cinematic scientific visualization. Both of us are computer scientists, but we both kind of have a bent toward design as well. We're super users of the Hollywood visual effects package Houdini, which we've been using for visualization since 2014. Kalina has written many pieces of external software to extend the capabilities of Houdini, and I was part of the Oscar-winning visual effects team that helped build the black hole for the movie Interstellar. So we're both part of the Advanced Visualization Lab, which is a Renaissance team made up of artists and technologists who work with scientists to create informal learning experiences for home television, science center, full-dome theaters, and giant IMAX screens. These movie posters are just a sampling of some of the films we've contributed to help communicate computational science with the public. I'm going to share a reel of our work now. If the playback is a bit choppy for you, there's a link to that in the course or in the tutorial resources as well. This type of visualization is geared toward what the National Science Foundation calls informal science learning. So the goal is not exactly to communicate facts and figures or what's called formalisms. That's the kind of thing that 2D visualization is really good at, typically a lot better than these 3D organic camera paths through data. The goal here is to help build metaphorical bridges to people's real-life experience through the visual language of film. There's plenty of evidence showing that people who witness these types of informal science experiences are more prepared to understand the topic later when exposed to them in formal environments. We also recently overheard a science collaborator telling his funding director that things that are good for public consumption are great for scientists as well. The science community often makes broad assumptions of its own contextual knowledge, and when they see our films, they still say things like, "I didn't know it looked like that." So there's definitely utility for these visualizations for both the public and for experts, but it's not really about finding numerical differences. So why are we teaching this tutorial in Houdini? I really love sharing this video, which is from a 2016 ad industry reel, because it shows why Houdini is unique among 3D animation tools. In the Hollywood effects industry, Houdini is primarily used for physics-based effects like explosions, collapsing buildings, magic sparkling ray beams, and so forth. There are two reasons it's so good at this. First, it has a non-destructive construction history, also known as a procedural workflow. The idea is that I can create an effect where I put balloons on a person dancing, and then if I don't like their dance, I can swap out that person without having to recreate the balloon effect from scratch. Second, it treats geometry types as interchangeable. Second, so I can move from a point-based effect to a line-based effect to a polygon effect to a volumetric effect and back and forth again with only a few simple operators. We found that these are extremely useful features, especially when working with large scientific data sets. Before we start looking at the software, I just want to quickly describe the paradigm Houdini uses for constructing scenes because it's significantly different from other graphics tools you might be familiar with. So Houdini is imagined as nothing more than a fancy file folder hierarchy. Every object you store and every operation you execute is merely a file in that structure. The entirety of a project in Houdini is imagined as a scene file, and every scene has these default folders that you can visit. For instance, the SOPs folder is for surface operators, so that's where geometry is. The ROPS folder is for render operators. The SHOPS folder is for shader operators. CHOPS is channel operators, and there's a bunch more of these folders. So for instance, inside the SOP folder, you might read in geometry, you might translate that geometry to some other geometry, and then you might apply attributes to the vertices, like a surface normal. So these are all operations that are represented as nodes in the SOP network, and each node has parameters that describe the operation that it's doing. You can see that even though all of this information is presented graphically in the Houdini interface, you're essentially writing a computer graphics program which allows immense flexibility for visualization. So now let's go ahead and get our hands dirty by opening up Houdini. Just a quick FYI, we are sort of juggling some technical difficulties. I think the VPN at our office has gone down, and I had a power outage overnight, and I'm sort of frantically pulling things back up again. But I think we can go ahead with the Houdini demo. Let's see. So I'm gonna share my screen now. So hopefully everyone will be able to see just this blank Houdini window. So please go ahead and open Houdini on your own machine as well. The goal today is to really work with everyone who is in attendance. We could blow through all this information in an hour if we didn't interact with you all. But we've run this tutorial several times in a live setting and are sort of accustomed to having people raise their hands and walking around the room and looking at people's computer screens and seeing what's going on. So we're really relying on your feedback through the Discord channels to kind of set the pace and to know when we've said something that is not obvious that we thought might have been obvious, or if there's just a hitch. I know, like, a lot of times our demo might look like what is running on a Mac computer, but if you're running on a Windows computer, you might have a slightly different interface. Also, because I just switched computers at the last minute, I'm actually demonstrating this in Houdini version 18 instead of version 18.5. So if anyone just downloaded the software today, you'll be running 18.5, and there might be some slight updates to the user interface. So again, I just want to point out, I think you can see on our tiny URL website, there is some updates about the Discord. When we first set up a Discord, we thought we were just setting up our own Discord, and then we learned that there's actually IEEE VIS
conference Discord, and so we switched to that. So please make sure that you're looking at the 3 channels we've set up on the IEEE VIS Discord server. And as I mentioned in the pre-recorded video, Kalina, me, and our colleague Stuart will all sort of generally be monitoring the Houdini questions channel. But feel free to also have conversation with other attendees in the general chat, and feel free to read through the tutorial tips channel for some sort of FAQ style questions. So we're looking at the Houdini interface, and it looks like there's a lot of stuff. Don't panic, it's really not as bad as it looks. The general layout is that you've got, I mean, at least this is the default layout, and you can change the layout to whatever you want. But on the left side, you have this 3D viewport, and if you just left click, you can tumble around that view just by dragging around. I can see it moving really quickly on my screen and not so quickly on the YouTube. So Kalina, please feel free to interrupt me at any point if it's not clear what I'm doing. I tend to sort of just go through a stream of consciousness, so I will not be insulted if I'm interrupted.
Will do.
Thank you. So left side of the screen is the 3D viewport. And then on the right side of the screen, in the bottom right, we have the network view. And so this is where we're kind of going to build our scene assets. This is where sort of all the magic, visual programming happens. And then up above, you'll eventually see is the parameter view, where we can set settings on everything that's happening in that network. So I'm going to go and just create an empty object in the network view. And to do that, I use the tab menu. So I hover my mouse over the network view, and then I hit tab, and this menu pops up. And the menu basically shows me everything that I'm allowed to do in that network view. So you can kind of scroll up and down with your mouse, and you can see that, like in test geometry, there's a bunch of sort of odd shapes that Houdini has provided for us. There's all kinds of wacky stuff. Houdini is a tool that we're using for data visualization, but it's originally a Hollywood visual effects tool. So there's a lot of stuff here for doing like visual effects simulations, which we talk about as being like based on the physics simulations that we tend to work with at the supercomputing center, but in Hollywood, if it looks good, it is good. Whereas in science, you want it to be accurate. So there's a bunch of stuff in here that's like more oriented toward visual effects. So what I'm going to do is I'm just going to use this tab menu, and I'm going to start typing the word geometry, and that's because I know that geometry is the sort of default container for geometry that goes here. And so when I type geometry and I hit enter, it gives me this little node, and then I can click it and place it in the network view. And you'll see that you have Geo1, and I can click on the name Geo1 and rename it to test geometry, for instance. And so it's important to know that what we're looking at right now is a container. It's not the actual geometry itself. And so if I double click on it and I go inside, you'll see that we are now inside an empty network. And this is where we would put surface operators. Like in the video, I was talking about that sort of file folder graphic. So right now we're in the SOPs context. We're in the surface operators context. And you know that because that's what OBJ up here at the top left of the network view means. So this is where like all the objects of the scene go. And actually, I'm gonna jump out of this geometry setting for a second and just talk about the different contexts in the network view. So if I click and hold on OBJ, you'll see all of the other networks that we can go to. There's OBJ, which is sort of the default. That's where you create your geometry. That's where you put your surface operators, your SOPs. But there's also the shop network. And that's where you put your shader operators, your shop nodes. There's the out network, and that's where you put your ROPs, your render operators. I'm not really sure why there's like two names for the same thing here, but out is for rendering, shop is for shading, OBJ is for geometry, for surfaces. And just to be clear, surfaces includes things like particles and volumes. It basically refers to sort of all the 3D elements of your scene. And then there's also this mat network, which is materials. And I'm still not super clear on the difference between mat and shop. I think that materials are sort of like constructed shaders with lots of promoted parameters. It's sort of like a more user-friendly version of shop, but you can actually put similar stuff in both of them. And I think the 4 of those are pretty much the ones that we're gonna talk about today. But as you can see, there are other ways to sort of interact with Houdini as well. CH is for channel operators, so that's like how you could pipe in sort of time varying animation curves. IMG is the compositor of Houdini, so there you can actually do 2D effects in there. And then stage and tasks, these are more like high level meta interaction with the software. So anyway, we're going to stay in OBJ, and you can see that we've dived into one of the folders in the OBJ context, which is this test geometry like folder or container, and we're going to create a sphere. So we're finally going to get to making something. So I'm going to use the tab menu and just type the word sphere, and you can see that the sphere option pops up at the top of the menu. I'm going to hit enter. And then that's going to give me this sort of highlighted box, and I'm going to drag it to where I want it in the network and left click, and that drops down a sphere, and voila, in the left side of the screen in the viewport, you can now see the 3D sphere. And what I was mentioning before, what did I do? Just have a green window. I think everything's fine. Okay, never mind. So everything's not fine. Have I frozen?
No, you haven't. Your video has, I mean, your screen share has.
Interesting. Everything is locked up. So I am attempting to click. I've heard that the best thing to do when you're having technical difficulties in a Zoom session is to just verbalize everything you're doing, just as a form of entertainment. I can hear my fan blowing pretty hard, so I think my machine is trying to do something that it wouldn't ordinarily be trying to do. I'm gonna check in on my other machine to see if it's up and running yet.
AJ, would you like me to share my screen and you could talk over it, things that I do on my end?
Yeah, let's do that. My computer is like frozen, like literally nothing's interacting with me right now.
Okay, I'll start sharing mine then, and if yours starts working up again, we can switch back over.
Are you able to kill my screen share?
I believe so. Yes.
Ah, nice.
Great. Okay, so here's Houdini. I'm going to get to where we were before. Here is a sphere. Now take it away, AJ. I'll try to follow along.
So I'm actually going to attempt to quit on the other machine. Wow, that machine is super borked. Okay, so I think I just force shut down my laptop, and now we're up and running on Kalina's machine, and we are looking at the sphere. Okay, great. So the next thing I was going to point out is the parameter view in the top right of the screen. So you can see that some of the parameters describing the sphere are visible. So right now, the sort of default version of the sphere is a primitive, and that basically means that it's the the simplest mathematical definition of a sphere. It's a constructive solid geometry is a term that comes to mind. You can see that the up axis is the y-axis, which is sort of not super meaningful with a primitive. But what if we change it to a mesh sphere instead? So now we're going to describe the sphere by a bunch of quadrilaterals. And now you can see that there actually is sort of an orientation to this sphere. The y-axis is coming out the north pole of that sphere, basically. So if Kalina were to change the orientation to z-axis, for instance, you could see now the sphere is oriented on that axis. Another thing in the parameter view is the sort of the shape of the sphere, and so you can change like the radius, like Kalina, what happens if you just double the x radius but not the y or z radius? So now you can see you kind of get this stretching, right? So you can start doing some interesting things. So actually one area where this gets to be a little bit more interesting in terms of creating scenery is working with the circle primitive type. So I wonder, Kalina, can you get rid of the sphere and instead put a circle in the network view? And so she just highlighted the sphere and hit the delete key to get that to go away. And so now we're looking at a primitive circle, but actually the circle is just so a primitive is actually a mathematical description of a circle. But let's go to a polygon circle. And so now it's just a series of connected lines. So it's an n-gon. So what if you needed to have a triangle in your scene? Well, then you go down to the divisions parameter and you change it from 12 to 3. And then you have a lovely little triangle. And let's say that you don't like the orientation of that triangle. In the arc angles parameter, the 0, if you change that 0 to like 30, I think that'll rotate that triangle to be sort of more parallel with the construction grid. So this is where the parameters on an object start being really useful, and you can sort of start playing with it. Like I've needed a triangle in the past if I was like trying to make a tree. Like right now we're working with a data set where we have we're sort of placing trees across a landscape where they've been identified by satellite, and so I'm creating sort of a single tree model that we're then copying all across the landscape. And as part of my single tree model, I have a bunch of low resolution leaves that are just triangles. And so this is how I made the triangle for that. I didn't have to go and like model, like draw a line in the shape of a leaf and then figure out how to make a surface out of it. I just used the circle geometry as is, and because it's far enough away from the camera, it's not really important that it's not something more complex. So let's see. Oh yeah, so I also wanted to point out that in the viewport, you can see in the very bottom left corner of the viewport, there's sort of this XYZ gnomon that tells you the orientation of your view. I think if anyone's familiar with 3D modeling and animation tools, you might also be looking for some other sort of familiar stuff. Kalina, if you go up to like the top right where there's sort of that big white square button, so that'll show you like single view versus 4-view setup. So if you go to the 4-view, you'll see that you sort of have your familiar perspective view in the top right, surrounded by 3 orthographic, side on and top down views. So if you're doing any kind of like 3D modeling task, that tends to be a really valuable way to do that. If you, I saw Kalina was mousing over the timeline bar at the bottom of the screen. So that's also something good to know about if you are planning to do any sort of time changing animation. In fact, why don't we just do a really quick little animation? Let's just get this triangle moving across the screen. So in order to do that, we need to set keyframes. For anyone who's unfamiliar with animation, basically a keyframe determines the position of a 3D object, or any object, I guess, if you're doing 2D animation. But the keyframe determines the position at a certain time, and then between 2 keyframes, the computer will sort of interpolate what the position should be, or whatever attribute should be. It doesn't necessarily have to be position either. You can animate the color, or you can animate the size. You can animate basically any of the parameters that you can see in the parameter view. So Kalina's already at frame 1. You can tell because the sort of black box on the left says 1. So let's set a keyframe where the triangle is right now. And we'll do that on, let's go up a level. So we're gonna come out of the sort of triangle shape parameters and see this container, the test geometry container. And every single piece of geometry will always have these same attributes: translate, rotate, and scale. This is sort of just a fundamental part of putting things in 3D space, is that they need a position, an orientation, and a size. We can animate the position, the orientation, and the size. So let's set a keyframe on the translation, just the translation. So if Kalina goes up to the word translate and right clicks on it, and then goes to the keyframe menu option and says set keyframe, that will set a keyframe at the current time at frame 1, and you'll see that all of the values that are now keyframed have this green highlight. You may have also noticed when she was selecting that through the menu, there's also a keyboard shortcut that's Alt left mouse button. So if you wanted to go a little bit quicker, you can just use that keyboard shortcut, or feel free to use the menu. It doesn't really make a difference. So in order to get it to move, then we need to set another keyframe. And so I'm going to ask Kalina to choose another frame at later in the timeline. I'll leave it up to her what time to make it. Okay, so we're going to go to frame 100. And so now the timeline is set to frame 100. You can see that the highlighting on the translation values has changed from a sort of bright green to a teal. And that means that it knows that you're at a different frame, but it hasn't stored any specific values at that frame. And so maybe if we just put I don't know, 5 in the X translation and hit enter, and then you'll see now it's yellow, which means that you have updated the value, but it hasn't been stored. And so then I'm going to ask Kalina to right click on translate and set a keyframe again. And I guess it's called commit change now. It's the same keyboard shortcut that it was before though, Alt left mouse button. And now you can see that everything's that bright green again, and you can see that the triangle has left the screen. Hey Kalina, do you want to switch back to just the single view? That'll make things a little bit clearer. Oh, I had skipped a really important step too. How do we navigate this viewport? Because now the triangle has disappeared from the view. So we talked a little bit about how the left mouse button can tumble the viewport. So you can kind of rotate around the center there. But we want to sort of zoom out so that we can see more of what's going on. And to do that, you hold down the right mouse button and drag across the screen. And so now you'll see this little sort of bidirectional arrow icon pop up. You know, we're moving inward and outward. And then the other mouse button that's worth knowing about is the middle mouse button. So if you hold that down, that gives you sort of this four-way arrow, and that allows you to pan across the screen, so to move things from side to side on the screen. One thing that always kind of caught me up when I was learning Houdini is that the viewport will sometimes get locked into this camera mode. So if you're having trouble with any of the things that I'm talking about, hit the escape key, and that may help you break out of sort of that weird mode that you can get stuck in. And then, you know, after you hit the escape key, left mouse button, right mouse button, and middle mouse button should help you navigate the viewport. Also, just sort of a small note, if you're used to using other 3D software like Blender or Maya or 3D Studio Max, a lot of those pieces of software require you to sort of hold a keyboard key down while you're using your mouse to navigate the viewport. That's not the case here. You just use your mouse keys and that's it. So I do kind of expect some questions about this interaction. So please feel free to say something in the Discord about it. And I guess Kalina and I are both busy, but hopefully Stuart is still there and able to answer your questions about it. So yeah, I think this is probably a good time to hop into some actual visualization demos. Am I missing any?
Yes, one last thing. We never finished talking about what to do with these keyframes.
Yeah, that's good point. We set our keyframes, but we didn't prove that they worked. You know, you can just drag your time around on the timeline if you want. So you can see now as Kalina drags back and forth that the triangle is in fact moving from keyframe 1 to keyframe 2. You can also use these little playback buttons on the left side of the timeline to determine you know, sort of well, a few things. So the far left one will take you back to the first frame of the sequence. The square one is stop. If you guys have a remote control, you're probably familiar with what a lot of these shapes mean. If you move to the right side of the frame number, there's this little step by a single frame thing. And if you go below that to the little forward and backward arrows with the green bars next to them, that means jump to the next or previous keyframe. And you can see that these green keyframes are also marked in the timeline, so you know where your keyframes are. And then so they've moved it in 18.5. But another thing to be aware of is that there's this little clock symbol in the bottom left group of buttons, and that actually limits the frame rate to real playback. So since Houdini does simulations, sometimes you want it to play back as quickly as possible because you just need to calculate the simulation, and each frame is like a step in the simulation. And that's why by default, the playback is just as fast as it can go. But sometimes you want to get the real sense of the timing of the final animated sequence. And in order to do that, you click this little clock icon, and it's called the real-time toggle. Real-time is a little bit of a confusing term in computer graphics, but in this context, what it means is it will play back as fast as it can, but it won't go any faster than the speed of your movie, which is something you can set in the preferences, but is by default set to 30 frames per second. So now if Kalina clicks play, it will only play at 30 frames per second, which is something that you probably won't be able to see too clearly over Zoom, but hopefully you can see that on your own screen. And I guess since I threw it out there, it's probably also just worth pointing out that there is a preferences panel. If you go up to edit in the very, very top menu, and then go down to preferences, you'll see that there's all kinds of different preferences. And Kalina, if you click on just general user interface, you can actually navigate from preference window to preference window with these little arrows in the top left of the preferences window. And so you can see all the many different ways that you can configure Houdini. One thing that I used to do is, oh, it's moved. Well, anyway, another thing just here on this first screen is this global UI scale. So you may have noticed when I was sharing my screen, the user interface looked a lot sort of skinnier and tighter. And for Kalina, it's a little bit more puffed up. And that, I think, it changes when you move from screen to screen. So Kalina's probably sharing on a display that she's not used to sharing on, and so everything's sort of blown up. Or maybe she just prefers to share it in a blown up look. But you can change that here with the global UI scale. So that's sort of one thing. If you're trying to make something happen that's not really working, that's where you do that. Feel free to close that, Kalina. And then the other thing that I want to point out is that if you hover over the viewport, it's very important that your mouse is in the right place. If you hover over the viewport and then hit the D key on your keyboard, D for dog, you should get display options. And this actually works in all of the different panels of the view or of the user interface, but typically the only place I use it is in the 3D viewport. But you can see that there's a bunch of useful tabs here for like setting up your environment. So so Kalina, if you were to go to, let's say, view, to the view tab, so this is where you can set your near and far clip planes for the viewport. If you're setting up a render with an actual camera, it's different. But for your viewport, if you're like trying to scroll in and things keep disappearing, it might be that your near clip is too big. And so to change that, you click on near and far clip planes. And I just say neither clip plane, and that allows you to edit it. And then, you know, I might change the near plane from 0.1 to like 0.001. And then I can get nice and close to something and it won't clip it out. And then another thing maybe is the background tab. If you're used to working in sort of a dark environment, you might change the color scheme from light to dark. Or, you know, if you're dealing with a data set that's brighter, then maybe the light background isn't doing it for you. So I'll sort of leave it as an exercise to the reader, clicking through all those display options. But just as a reminder, that's the D key while your arrow is hovering over the 3D viewport. Okay, now Kalina, what have I left out of the sort of the general overview?
I think we should move on to the demos because we're going to be having a break in 45 minutes.
Okay, great, perfect. Let's do it. So hopefully you all have downloaded the files that are on that course or tutorial website. There's a zip file that has a name. Do you have that handy, Kalina?
I do. I'm trying to, I'll share my whole screen and I can show people. Whoops. So, right. IEEE VIS Houdini is the folder you should have downloaded, hopefully in your downloads folder or somewhere where you are aware of. And the first file we're going to look at is the mocap demo, which starts with the number 1.
Yeah, so feel free to just double click on that file and it should open in Houdini. And I'm going to just take a breath here while everyone opens that, because when we've done this live before, we tend to have a lot of you know, it's not working. There's, you know, something weird about my installation. There's something weird about the file. It's possible that you might get like a little error window pop up that says like can't find so and so parameter. That should be fine. There's typically nothing too bizarre about this scene file, so it probably should just run. I'm also sort of working on pulling my little control center back up. So in theory, I should be able to see your questions. Okay. Here we go. Okay, so I'm looking at the Discord channel and I'm not seeing any questions yet. So I'm just assuming that everything's going great for everyone. Please, please, please drop a question in there if you have one. So we're basically looking at a quick demonstration of stream tubes, which are a really common 3D visualization sort of tool, sort of a visual metaphor for movement over time. So again, we've got sort of all of our geometric assets in the network view in the bottom right. You can see the bottom of those two so both of those are containers, remember, they're not the geometry themselves, and they both have that translate, rotate, scale, like I mentioned, all geometry containers will have. The bottom of those two containers describes the motion capture geometry of this running man, and then the top container contains the sort of tracking dots and the stream tubes or streamlines that are following him. I did not create the motion capture man. The motion capture man is a feature that comes with Houdini. If Kalina hit the tab menu and started typing mocap, I believe you will see that there are actually several mocap options. I think I have mocap biped 2. So you can feel free to mess around and drop down any of these mocap objects into your network view. But for the time being, we've got one that's already built. And so we're going to go ahead and work with that. So Kalina, if you dive inside the mocap biped, you'll see that there is this whole network of nodes. And basically, this describes the skeleton of the motion capture man. Remember, this is all pre-constructed for us in Houdini. But if you zoom way in, you can see that each of these are connected to like a different bone. And so this is how you sort of animate the man, is by putting a virtual skeleton on him, and then sort of behind the scenes, that skeleton is getting attached to the mesh, which is, you know, referred to as the skin, and then it makes this, you know, 3D geometry run. So in order to make the streamlines, I decided let's just follow a few of his joints. So I went hunting through this network to find his 2 wrists and his 2 ankles. And I'm not going to make Kalina do that. Oh, look, I think Kalina found an ankle. But you know, you don't have to go digging around because I've already done it. So if you bounce back out to the object network and then into the tracking dots network, you'll see that there's sort of this row of 4 nodes that are object merge nodes that have these 4 joints that I'm talking about. So just a quick FYI, what an object merge node does is it brings geometry from one geometry network into a different geometry network. And so that's what we're doing here, is we're grabbing the joints from the pre-constructed motion capture man into this tracking dot network. So we've got one for left wrist, one for the right wrist, and so on. So then each of these joints feeds into a little stack where I have created an add node, and the add node basically puts just a single point where the joint is. And then a delete node, which gets rid of the joint. So now we've just got 4 points that represent the four joints.
I have a question, AJ.
Yes.
How can we look at one of these nodes individually? Right now we're looking at everything.
Oh,
Is there?
good call. Good call. So I haven't even gotten into the blue flag yet, which is super important too. So first thing I'm going to say is if you can go up to the top right of the viewport, and there's like these 3 3D shapes. There's like a cylinder, a cone, and a sphere. Sorry, a little bit to your left. A little bit higher up. One up. That one. Yes. So that currently we're showing all objects in the scene, all containers in the scene are visible. But let's look at just this network. And so to do that, we're going to hide other objects. So now the motion capture man is gone and we're looking at the stream lines. But I'm describing points to you, not lines, right? So why are we seeing lines? Well, this blue flag that you see down on convert 1, that blue flag basically means show this node. So you can never have, I don't think you can have more than 1 flagged at a time. Maybe you can. That changed. But we're going to pretend like you can only have 1 thing with a blue flag at a time. So Kalina, if you go up to that delete 1 node and hit the blue flag on that, now you can see that we're just looking at that 1 point, and it's this tiny little speck. Kalina, if you click that little ball icon on the right there, yeah, that'll make the dot just a little bit bigger. This is just a little trick if you're working with point clouds a lot. That display points button just sort of makes them a little bit larger. And that those display settings that we talked about, you can actually change the size of the point display, so that, you know, when you have a point cloud, things don't just vanish into infinitesimally small pixel-sized dots. So that is the way to look at the left wrist dot. But what if we want to see all of them? Well, then we move down the network to where there's that merge 1 node. And so that's bringing together all 4 dots. And so now you should see all 4 of the dots together. And I'm actually going to backtrack slightly and point out that the 0.1 node is applying a color to the dot. So there's a lot of things you can do with the point node. In this case, I'm just using the add color function. There are a lot of ways to add colors. There's a color node. There's also a lot of ways to change point attributes. There's a sort of a scripting interface that they're actually they tend to be preferring these days anyway. But the point node works just as well. All you're basically doing is you're placing a color value onto the points. So I think this might also be a good time now to start talking about the information window. So Kalina, if you hover over merge 1, you'll see there are a bunch of different options here. So the eyeball shows you the blue flag, right? So if you click that, that's another way to turn that blue flag on. Yeah, if you switch it, there you can see now you're moving that visibility blue flag. In the upper left is that little yellow down arrow, and that means bypass. So that means don't use this node, which is a little bit of a weird situation with a merge because it's bringing a bunch of different paths together. But well, I don't know, if you selected like a whole stack of nodes and bypassed it, maybe, Kalina. So if you just like drag over that whole column and hit bypass, it'll actually bypass all of them together. And this is like a really nice little time-saving trick, is if you highlight a bunch of nodes, you can do the same thing to all of them. So now you can see that when she turns that on and off, the point there disappears and reappears. So that's the bypass flag. Then there's also the template flag. So maybe if you, Kalina, why don't you template the bottom node, the convert1 node? So we'll keep these 4 points as the blue flag, but then we'll do the pink flag on the convert1. And so you'll see now the template basically does sort of a ghost view of another part of the network. And you can sort of shift select in the template with the template flag on multiple nodes. So you could have lots of different things sort of ghostly in the background, but still only have that blue flag determining what's actually like the primarily visible object. Okay, so those are sort of just some usability flags. We can turn that one off, that template off. So now if we go back to the merge node and we hit that eye on the left, this is our little information window, and this is so useful when you're doing visualization work. So it'll tell you very specifically what's happening in your scene, as compared to, sort of just the general visual feedback you're getting from the 3D viewport. So you can see right now that when we've merged together the 4 points that represent the 4 joints, you can see that they're taking up 9 kilobytes of memory. You can see sort of the bounding box of those 4 points with the min and max and size. You can see like the center of mass of those 4 points. This is also, if we were working with volumetric data, this is where you would see like the resolution of your volume. Especially when you're dealing with big data and you start worrying about the size of things, this is where you get all that information. And this is also really great at debugging. Another place that's really great at giving you information and debugging is I'm jumping over to the geometry spreadsheet now. So this is in that menu above the viewport. The geometry spreadsheet tells you all the information you could ever possibly want about your geometry. Well, if you've stored that information on your geometry. So you can see, actually, Kalina, why don't you, so important thing to know about the geometry spreadsheet, it's not showing you the geometry that is blue flagged, that's visible. It's showing you the geometry that has that yellow outline that's highlighted. So if Kalina moves around the network with the highlight without changing the blue flag, you can see that the geometry spreadsheet is updating. So so I was going to suggest if you highlight one of the delete nodes before the point node, you'll see that there is this point position attribute, px, py, pz, but there's no color attribute. And then when you highlight the point node, when you move further down this network, now the color attribute appears, because that's what that point node is doing, is it's adding a color attribute. So I guess another thing to know is that in that geometry view, sort of next to the words node point 1, there are these 4 buttons. Right now, the sort of default is to always look at attributes that are stored on points. But there are attributes that you can store on entire meshes, and that would be like a primitive attribute. And then there are attributes that you can store on entire sort of containers, and that's a detail attribute. And so that's sort of, we're working with a pretty simple data set right now, but eventually you might be working with data where you flip between all these different contexts in the geometry spreadsheet. And then Kalina, if you highlight the merge node again, so we have sort of multiple data points. If you click at the top of any of these columns, it'll sort the data set or the point cloud by that attribute. So you can see that she's sorting by the highest Y position and then the lowest Y position. So you can actually toggle high and low as well by clicking a second time. And this is just a way to sort of be able to check your data. Like let's say that you weren't looking at position and color, but let's say that the points had a temperature attribute. This would be a way for you to quickly check what your lowest and highest temperature values are just by toggling that column. Okay, so now back to the network. Let's bounce back into the scene view, Kalina. So we're looking at these 4 dots, but we want to see how those dots evolve over history. And so in order to do that, we're going to go and highlight that trail 1 node. And this is sort of one of these nodes. Sometimes Houdini has nodes that are just like addition, which is like pretty straightforward. And then sometimes there are these magic nodes that seem to do everything you want in one step, which is really great. And so what trail does is it's this magic node that just drops down basically a copy of your geometry at every sort of state it was over the past, n number of frames, which in this case, you can see in the parameter view has been set to 20. So if you changed from 20 to 10, you could see the number of points goes down because we're only looking at the past 10 frames. I guess it's also relevant that so right now Kalina has the timeline at frame 12. So she can only go back 12 steps, right? There's nothing before frame 1. So if you were to drag it further, say to frame 20 or 30, then dragging the trail length around makes more sense, because you can. That was a good demonstration too, Kalina, is that as she passes frame 20, the oldest points cease to exist because we're only looking 20 frames into the past. So this is pretty cool, but it doesn't look super cinematic. It's hard to sort of understand what you're looking at unless you connect them with a line, and that's what that next node, the add 3 node, does. If you look at the parameters there, you can see that we're creating a line by selecting that polygon tab and then going to group, and we're skipping every 4th point. And so essentially that just means in your point cloud, there's 4 lines, and so every 4th point belongs to line A, B, C, or D. And so now we've got this sort of nice line, and like that would be great for video game graphics, but we're trying to make movies here. And so I used a convert node to smooth it out and convert these polygon lines into smooth NURBS lines. And so Kalina, if you zoom out again and maybe visualize the man, the mocap man again, you'll sort of just get, and then drag around the viewport, you can kind of see how those lines follow him. And as you pass frame 20, they sort of trail along with him. And typically when you're doing streamlines, you don't want an infinitely long trail. You do want it to sort of end at some point, or you just kind of get a clustered mess. So yeah, Kalina, remind me what time we're aiming for here?
We have 29 minutes until the break.
Okay, gotcha. Great. Okay, so I think this is a little bit slow because I'm trying to get like the user interface stuff in with the visualization stuff, but it's going to pick up a little bit as we get into some of the other visualization things. I guess I will point out in the node network as well, there is sort of this little hanging thing over there with the sphere 1 and the copy 1. So this is basically geometric point instancing, which is another super handy tool that Houdini handles pretty efficiently. I tend to be able to do this with like 1 million points easy, 10 million points with a little bit of weighting. I wouldn't recommend, unless you have like a really souped up machine, pushing it much past that, because this is also, for anyone who knows what I'm talking about, this is actual geometry instancing, which means that you're creating copies of your geometry. But there's also render instancing where you create instances at render time, and that's much more efficient. And so I would generally recommend that unless you need to see the copies in order to design your scene, that you not do this geometry. You not copy things in geometry, but copy things in the render. So long way of saying, Kalina, if you visualize that copy 1 node, that's coming from those 4 joint points. And you can see now that I'm dropping a sphere onto each of those points. And if you scrub along the timeline, you'll see that those spheres kind of keep up with him. It's basically just placing sphere geometry onto those points. You know, if you use the tab menu to drop down a teapot and swapped the teapot in for the sphere, you would excuse me, you would see, is there a teapot? Oh, I think a teapot is in a geometry called like render, or called like primitive or something. The pig head is good too. The pig head is maybe even better. Maybe if you use that uniform scale to take it down a bit. So yeah, so now we've got a pig head at each one of his joints. So yeah, this is one of those tools that you'll use a lot more than you think you will, and maybe you already think you will use it a lot. You'll still use it more than that. So just something to be aware of. And I'll also point out something I meant to mention earlier is, Kalina, if you go back to the object view where all the geometry containers are, all geometry containers have translate, rotate, and scale, but you can see that these geometry containers have different attributes beyond that. And that's because the motion capture man, the sort of the pre-built asset that Houdini has created for us, they've done what they call promoting attributes. So basically they've taken something somewhere in the inner network and pushed it up a level to sort of the dashboard of the container. And so basically you can change his animation from running to sit and cheer, and the whole network will update. And basically all you're doing is you're when you change it to sit and cheer, you're changing one of the attributes inside the mocap biped 2 network, and then remember, tracking dots is importing the joints from that network, and so you can see now the pig heads are following the joints of the new animation in the same way that they were following the running animation. And Kalina, actually, can you switch back to the streamlines? Since we're trying to show visualization, I'll just prove that our streamlines are now following the sit and cheer animation instead of the running animation. And maybe sit and cheer isn't as interesting of a animation to trace as like a walking animation, or something else that's on that motion capture man. There's also some different textures that you can apply to the man if you don't think that he looks good. They've got a variety of different looks for him. This, I think, one of the intentions of this asset is that you could create a crowd of humans, and so of course having a zombie texture is an important thing. This is where you start to realize that you're working with a tool that's not just for visualization. Okay, so anyway, I think that's a really, really thorough overview of this motion capture scene. Why don't we bounce into the Antarctic scene? Yeah, Antarctica demo. So this would be a good time, if anyone has any questions, to please let us know what those are. Okay, so, sorry. And I see a question in the Discord. What's the difference between points and vertices? This is a fine nuance of computer graphics. So my understanding is that a point is like if you imagine like a 3D sphere that's made of triangles, the point is everywhere that any triangle meets. The point is a dot that connects faces in a 3D geometry. A vertex is unique to each triangle. So if 4 faces all meet at one point, that point represents 4 different vertices that belong to 4 different faces. And so that's like especially important when you're working with UVs, when you're doing like texture mapping from a, you know, a 2D image to a 3D object, 3 faces, is that you want, you know, you want to be able to separate the 4 corners of a quadrilateral, so that you can map that to your texture, which is why the vertices of that face are unique, but the points are not. So they sort of function in similar ways. They're both, you know, they both don't have size, right? They're both infinitesimally small. They're both an XYZ position, but the point sort of represents that position only. And like one thing you'll notice in Houdini is that if you put a color on a point, and then you put a color on an adjacent point that's different, the color will actually fade across the face from the color on that one point to the color on the other point. Whereas if you put the colors on the vertices, you might get like very hard transitions of color from face to face. So hopefully that sort of answers that question. Okay, so Antarctica demo. So what we're looking at right now is this big fancy plane. There's nothing super interesting happening yet, but that's because we haven't applied our data. So what we're going to do is we're going to dive inside this pre-constructed Antarctica network here, and you'll see that there are 2 networks coming off of this. Also, remind you that in that file folder graphic that I shared in the pre-recorded video, Houdini is just a series of nested directories. And so what we're going to do is we're going to dive 2 levels deep now. So we create a grid. That's just Houdini's word for a plane, just a flat piece of quadrilateral geometry. And then we're gonna change it. And so let's dive inside apply data to grid first. So we're just gonna do sort of something a little bit simple and then make it a little bit more advanced after that. And actually, Kalina, can I ask you to visualize that node? We'll just go ahead and apply it and see what it does and then understand why it's doing what it does. And you can see that it's a little bit slow because it's actually reading in a pretty big image and putting it on a pretty high resolution geometry. So don't panic if your computer is a little bit slow at making this happen. But basically what we're doing is we're applying a digital elevation map of Antarctica to this plane. And so now you can see the outline of Antarctica. And I think it might be like mirrored in a weird way or something, but we're not gonna worry about that right now. So if you dive inside this network, this is what's called an attribute VOP, V-O-P, V like vertex. And so what that means is it's a VEX operator. And if you remember, wait, I don't think I've said this yet. VEX is Houdini's sort of internal scripting language, VEX. And so this is sort of a visual representation of that scripting language. Later, Kalina will talk about VEX as sort of a written language as well. But yeah, so in terms of the visual version of the VEX language, you can see that. Actually, Kalina, can I ask you to do another thing? Can you create a new attribute VOP, just a blank one? If you bounce out of here and just drop down, you can see again using the tab menu, and then go over to attribute VOP, drop it down, and then dive inside. You'll see that it comes with two nodes already because it knows that you're going to want to work with these nodes. The first one is sort of your input, and the second one is your output. So if, for instance, Kalina wanted to move all of the points in the network, she could drop down an add node and then pipe the P position from the input into the add node and pipe the output of that back into the output P. P here means position, and so it's basically running a loop. What this attribute VOP does is it runs a loop across every point in the network, or sorry, every point on the geometry, and applies the same functions to it. And so then if you middle mouse on input 2 in that add node, that'll give you a few sort of, you can also just use the tab menu to drop down a constant, but this is a sort of a trick I use to drop down a constant node, and that's just if you just want to add a single number. And then yeah, go ahead and change that to so actually this might be a little weird because the position is a 3-channel attribute, px, py, pz. And so Kalina is showing you how to change this constant to a vector to have 3 floats. And so now if we add 1 to the x channel, in theory, oh, you know what's happening though is we're not visualizing the VOP. It might not even be connected. Right. So let's connect it to the grid and then visualize it. And now you can see that the entire grid has moved sort of 1 unit in the x direction. So that's like a drop dead simple attribute VOP. These VOPs can get really complicated if you are a glutton for punishment. But if we go back into the apply data to grid attribute VOP, what you can see we're doing is we're applying color to every point based on a data set. And so the way that we're doing that is we are piping the position into a vector to float node, and that's just separating the 3 attributes, the 3 components of the position into their XYZ components. And then we are dividing each of those by the sort of the resolution along that axis. And those little knobs I'll come back to in a minute. But basically, all you need to know right now is that what these divide nodes are doing is that they are changing a real world position into a sort of percentage. So we're getting sort of the distance along the x axis and the distance along the z axis in a 0 to 1 sort of number. And then you can see with the Z, we're also complementing it, which just means that we're flipping it. I probably did that just because things were mirrored. And then you pipe those into this texture node. Here in the texture node, they refer to the UVs of the image, of an image, as S and T. And so basically these are UVs, if you're familiar with UVs. UVs are basically how you map textures to 3D geometry. And then again, I'll get back to this knob, but basically that knob is determining what the image we're actually reading in is, what our data set is. And the output of that texture node is a color. It's, you know, what the color of the texture is at the UV position that you've given it. And then we just simply pipe that into that sort of pre-existing output node that has a CD attribute, which thank you, Kalina, for hovering over that. You can see CD is the built-in sort of name for point color in Houdini. So so when we get into like scripting things by hand, this is actually a nice way to sort of learn some of the variable names, because you can see them just written in these pre-built input and output nodes. And so yeah, so in order to change the color here, we are assigning the values to CD. Okay, so now getting back to those knobs, what I've done there, this is what I referred to earlier with the motion capture man. I've promoted those attributes up a level. I don't want to have to keep diving into the network and out of the network in order to adjust things. And so if you hop out, like Kalina has done, and then highlight the node. And remember, highlight is the yellow outline. So that's just a single click in the middle of the node. You can see now these 3 attributes have been promoted. And so in the texture map attribute or parameter, sorry, I've put the location of the data set. And this, if you're having trouble, this is maybe a point at which you would debug the location of the image. The image should have been in that zip file that you downloaded. So if it's not finding that, you can click that little box or icon on the right of the file name, and that'll give you a file browser, and so you can go hunting around and trying to find the data set. You can also swap in any of your own favorite images. Right now, we're just reading in a color and applying it to the polygon, so it won't really mess anything up. I should also mention that $hip is more Houdini shorthand. This is one of Houdini's macros where they do sort of a $sign and then some capital letters. In this case, $hip refers to the file directory location of the scene file that you're working in. So basically, when we were creating this tutorial, we used $hip as the directory where we put the scene file, and then we created the subdirectory inside that for the data sets. And so in theory, this should just run fine on your machine as is if you opened the scene file in the folder that it downloaded in.
Right. I have a quick notice that there's 11 minutes left until the break.
Okay, great. If we get cut off, maybe we can catch up later. Sorry that everything's sort of been a little scattered. We didn't expect that Kalina was going to be my hands during this, but I think it's working out all right. So thank you, Kalina, for being so helpful. So then the other thing to sort of show off is that if you click on the word X division or the word Y division, I've actually put expressions in there. And so this is like another little scripting tool in Houdini. Basically, we're taking an attribute from one node and putting it into another node's parameter. So in this case, excuse me, we're using that grid one node and we're grabbing its size, and that's its size in terms of divisions. So yeah, if you click on grid one, you'll see and there's actually expressions all over this as well. Just FYI, the reason the grid is the size it is because I looked at the actual pixel resolution of the image just in my file browser, and I saw that it was 6,875 pixels by 5,625 pixels. And so, Kalina, if you click on size, you'll see that I think I divided both of those pixel values by 1,000, and that was just because I thought this was about the right size for it in the viewport. And then I took that size and divided it by 2 for the center, so that the corner would be lined up with the origin instead of having the whole plane centered at the origin. I'm not really sure why I did that, but we did it that way, so that's what it looks like. If you want to do this too, one thing another sort of neat Houdini trick is you can copy a channel and paste its script by right-clicking on that channel. So for instance, size, and going to copy parameter. And then if Kalina goes to perfect, center Y and right-clicks and says paste relative references. Oh, yep, there we go. So paste relative references. That immediately drops that script in. So now the center Y parameter is pointing to the size X parameter. Obviously it screws things up because it's actually an active network. So I will ask Kalina to then right click on that and say delete channels. And now you'll see that it leaves the value there, but it gets rid of the script. And to return it to the default, you can right click on it again and say revert to defaults. So these are some neat little tricks with playing with geometry parameters that I do all the time. And it seems a little complicated at first, but I promise after the first 1,000 times, you will have no problem remembering it. So anyway, then I thought I'll use the pixel resolution again to determine how many rows and columns there are in the grid. But I thought 6,000 columns and 5,000 rows, or sorry, 6,000 rows and 5,000 columns was a bit much, considering I don't know how much processing power everyone's computer has. So divided that by 5. And when Kalina clicks on the word rows, you'll see that math evaluates. This is like a really great way if you just don't want to pull out a calculator, you can just type your math right into the field. Sometimes I want to like test a value and then I want to test another value. And so I'll literally say like value A times 0 plus value B. And that's like a really dumb way to just store both values there so that I don't forget what the original one was. So it's just sort of like a handy little thing that pretty much any parameter in Houdini you can just type some math into. So yeah, so then we pull that number of rows and columns over into the attribute VOP, and that allows us to figure out sort of the position divided by the number of divisions tells us our percentage along the axis. So this is still not a super interesting data visualization until we go to the third attribute VOP there, the displace and color. So I'm going to ask Kalina to blue flag that, and maybe even tumble around the viewport a little bit so you can really see that it is now a 3D data set. This is because the image isn't just black and white where there is land and there isn't land, but every pixel value has stored a different altitude above sea level. And so when we apply that with this attribute VOP, we're actually pulling polygons off the surface of the grid. And actually, this is severely exaggerated already. You can see sort of the spikiness in the foreground here. This is a mountain range along the coast of Antarctica. Those mountains are clearly way too tall. But for the sake of being able to see what's going on, we sort of exaggerated the height. So, Kalina, if you dive inside this attribute VOP, we'll be able to see sort of the same thing happening as we did with the color. We're figuring out our UVs, we're piping them into texture. The texture is being read in at the higher level. But this time, instead of just piping the color of the texture into the color of the points, we're piping the color we're using the color as data now. So we use a vec to float, and that's gonna separate the output of the color, which is originally a red, green, and blue channel. Although we're dealing with a black and white image, so red, green, and blue are sort of irrelevant. Red, green, and blue in a black and white image are all equivalent values. So we're just gonna grab the first value. We're just gonna grab the red, and then we're gonna pipe it into two different things. The top thing is this fit1. So a fit is just like a lerp. It's just taking a value in one sort of range of numbers and transforming it into a different range of numbers. So I happen to know that the digital elevation map has a maximum value of 4,000. So I'm going to take the 0 to 4,000 range and squash it down into 0 to 0.5. And so and then I'm going to pipe that into the position of the polygons, specifically the Y component of the position. And now if Kalina drags around that 0.5 in the fit node, you'll see that it might be a little laggy, but you can see that 0.5 basically is defining the height of the geometry. So if the digital elevation map were stored in meters, which I think it might be, and your scene was in meters, then you wouldn't even need to do this remapping, this fitting. But because I've sort of gone with units of pixel instead of units of, units of 1/1000th of a pixel instead of meters, we're going to do this remapping to just kind of get a visual match. So getting things to sort of pop off the surface is really cool. but also driving color with data is a super big part of data visualization, as I'm sure you all know. And so these color ramp nodes are things that are just all over the place in our scene designs. So we're basically fitting again, but this time we're going to fit from 0 to 4,000 to 0 to 1 because we want a percentage. This isn't like an absolute value like the other one is. Like the other one was lifting points off the surface by exactly 0.5 units. Here we're just looking for a percentage. So we're going 0 to 1, and then we're piping that into a ramp, which is called a ramp parameter. Kalina, can you tab menu and type ramp parameter? There's actually another node called ramps that you do not want. That is a different thing. So make sure that you're selecting the ramp parameter node. The other thing to know about the ramp parameter node is that it comes in RGB format and it comes in spline format. And so we want the RGB in order to drive the color instead of like a single channel attribute like transparency. And then we pipe that into CD, which we established as our color before. And what the ramp parameter node does is it automatically promotes the ramp higher up. So you'll actually, before you go up, Kalina, if you scroll down in the parameter view, you'll see that there's a default ramp. That's not live. That's literally just what happens if you don't have a value yet. The actual live version of the ramp is promoted up a level. So if we bounce out of this VOP, we can see that there is a color ramp here. And I know we're running out of time, but Kalina, if you just drag some colors around, you'll be able to see that these colors kind of go up and down the altitude data of the sort of the Antarctic continent. And so this is a really good way to sort of just quickly prototype geometry. And all of this stuff can also be produced in shaders, which allow you to sort of decide what things look like at render time. So again, I would recommend like not going too over the top with this stuff in the geometry network because it can get really laggy. Whereas if you do it in shaders and at render time, everything is much faster and more compute efficient. Oh, and thanks. She's also changing a color for us so that we can prove that it really is in fact live. Okay, so there is a third demo. I think we're gonna forego that for now. I might bounce back to it later, but I know that it's break time, and I will try to use this break time to bring my computer back to life. And I think at 10 a.m. Mountain time is when Kalina will take over and start talking more about scripting and programming stuff. Did I cover everything, Kalina?
You did great, yes.
Okay. All right, well, thank you, everyone.
Oh, that's fine. Sure. So 9:45 is when the tutorial starts back up.
Okay, yeah. So just to be clear, that's not break then. That is the next part of our presentation. So don't miss that. Okay. Thanks, everyone.
Taylor-Coyer flows is a turbulent fluid motion created in the gap between the two rotating cylinders. The traditional reason-based methods are only able to capture the small-scale coherent structure. The detection of the large structure depends on the 2D cross-section, which is not the true configuration. We adapt the feature-level set methods and the density estimation to combine multiple attributes and use them as the filter to separate large and small-scale structure.
Confusion flow is an interactive visualization for the performance analysis of classification models. It introduces a novel temporal adaptation of the confusion matrix, which lets model developers compare the learning behavior of multiple classifiers over time. Find out more about confusion flow in our talk or in our TVCG paper.
How do you visualize the nanoscale, 1/1000th of a meter, for the public? As part of a Science Center exhibition, we developed an immersive environment that explains nanoconcepts by allowing users to explore nanoproperties. We reflect on how exploration, the confluence of explanatory and exploratory visualization, can be applied to visualization in public spaces.
Digital humanities present great opportunities for testing new visualization approaches and evaluation techniques. However, and given the diffuse character and novelty of the field, it may also be intimidating for novel and senior researchers willing to get started in the discipline. In this paper, we propose a data-driven analysis of visualization for the digital humanities to identify key themes, authors, and relevant publications. So if you want to know more, please read our paper.
A testing environment for continuous color maps. Many other fields in the computer science do it, we should do it too. With our work, we introduce the approach of using test functions as a standard evaluation method. We present a test suite for continuous color maps implemented in the CCC tool. Adapt the task to your requirements at the interactive testing section and observe them at the testing evaluation section.
In our current work, we visually compare two cohorts of segmented and classified tissue images, originated from single-cell omics data. To that end, we developed data-driven and interactive workflow implemented in a multi-linked view system. Finally, we show the effectiveness of our workflow through specific case studies.
Scatter plots and parallel coordinates are widely used for visualizing multivariate discrete data. However, for multivariate continuous data, the continuous scatter plots and continuous parallel coordinates are more suitable. In this work, we extend them to uncertain data. Additionally, we also extend fibers to uncertain data. If you are interested, come to our presentation.
We present the first generic design space and library for visual piling. Inspired by physically piling paper documents, visual piling describes an interface for spatial organization of visual artifacts into piles of partially overlapping items. Piling affords interactive grouping, arrangement, previewing, browsing, and aggregation to reduce the complexity and support comparison of large collections of small multiples.
Deep neural networks are vulnerable to maliciously generated adversarial examples. This brings high risk in applying these networks to safety-critical applications. We developed a visual analytics approach to explain the root cause of such wrong predictions. Our contribution contains a constrained path extraction method, a river-based visualization, and a contribution analysis method.
CMed is a visual analytics framework for exploring medical image data annotations acquired from crowdsourcing. CMed can be used to visualize, classify, and filter crowdsourced clinical data based on a number of different metrics such as detection rate, logged events, and clustering of the annotations. CMed provides several interactive linked visualization components to analyze the crowd annotation results for a particular video and the associated workers.
Several recent studies advocated the use of non-parametric density models for the improved characterization of data uncertainty. The non-parametric models, however, present the challenges such as increased memory and computational requirements. In this work, we propose an efficient non-parametric framework for volume rendering in the context of uncertain data and show their effectiveness in classifications via comparisons with the other statistical models. Morse complexes have shown a great utility in understanding the topology of complex scientific datasets. The noise in the scalar field, however, can significantly distort the Morse complex topology. Hence, we study the extraction of Morse complexes for ensembles of noisy scalar fields through their uncertainty visualization using our proposed statistical summary maps.
Asteroids have always been and will always be a threat to life on Earth. Most likely, an asteroid will hit deep water, but what properties will actually lead to a threat like a tsunami? Ensemble simulations are a common tool to understand the effect of different parameters like the size of the asteroid. We propose an interactive visual approach to help analyzing deepwater asteroid impact simulation ensembles.
We present TransVis, a design study that is proposed to analyze and integrate close and distant reading of multiple translations. TransVis presents the overview of the collection to capture global patterns that is facilitated by the ADM-VIV matrix. TransVis integrates a detailed view to explore interesting path of alignments. We also propose the TLC view to examine and explore the terms of the user selected path to justify and reason the AD analysis.
We have seen many visualizations for tree data structures, but when showing changes in trees over time, some focus on displaying hierarchy, while others highlight their changes. With split streams, we combine two approaches and their individual benefits. We evaluated our method in a user study and consider it a general-purpose method for the visualization of dynamic hierarchies. Our JavaScript library is openly available.
Now that we know how Houdini works and how to use it, let's talk about loading in scientific data into Houdini. There are a few different ways to do this, the most straightforward of which is a direct import. If your data file is in one of the file formats that Houdini can natively read, like CSV spreadsheets or OBJs or image files, it's really straightforward to read. Here is an example of reading in a CSV spreadsheet. All that you need is a table import node. Here you can see I've specified the CSV, the number of attributes or columns in my spreadsheet, and what column number corresponds to which attribute. More than likely though, your data files will not be in a format that Houdini knows how to understand, so another option is to build a custom C++ plugin as a data reader. And in fact, if you were to go out and Google how to get data into Houdini, the top result you would get would be the Houdini Development Kit, or HDK, which is exactly that. So this tells you how you can build your custom data reader plugin. This is often overkill for just reading in a single data file. This is very well documented, and there are lots of good reasons that you might want to use this, but there are also some downsides. So let's first talk about the pros. As you build your plugin, it ends up being integrated seamlessly into the Houdini user interface, which is really nice. It's a slick kind of feature. Plugins are extremely powerful. You can pretty much think of anything that you would want Houdini to do, and you can use the HDK to build a plugin to do just that. But on the downside, this is a lot more programming intensive than some of the other solutions that I'll be talking about. Because you do need to know how to code in C++, and if you're a newcomer to programming, C++ isn't necessarily a place that you might want to start. There's also maintenance, so every time Houdini releases an update and a new version of their software, you're going to have to revisit your plugin and update it as well to make sure that it's still compatible with the new Houdini version. So another option is using this open source tool that we at the AVL have developed called Houdini. And Houdini, the name comes from the combination of YT and Houdini. If you're not familiar with YT, it's a scientific analysis and visualization Python package that's often used in astrophysics, but it can read volumetric data of other sciences as well. And the way Houdini works is that it uses YT as a data reader and converts your volumes that you read in into a format called OpenVDB, which Houdini can ingest. So the reason that we use YT as a data reader is because YT already understands many different volumetric data formats, so you don't have to write a custom data reader for each new format that you encounter. So this really speeds up the process. To explain a bit more about this OpenVDB format that Houdini likes, if you have a volume like this, so here's a tornado from the top down, there's often a lot of empty space in a sparse volume like this. And traditional Houdini volumes that aren't OpenVDB would still fill every voxel of this data set with 0 values, effectively taking up a lot of memory where there's no data. But OpenVDB is a bit more scientific, kind of like AMR, maybe not exactly as sparse, but it does let you more efficiently store sparse data. So the final way that I want to talk to you about is scripting. Houdini is very script friendly in all different parts of its interface. So the easiest way to do scripting in Houdini is not necessarily how you'd want to load in data, but just as an example. You can write little scripts, or as Houdini calls them, code snippets, directly inside the parameters. So here, for example, I'm translating by 1 in X, but in Y and Z, instead of putting in actual numbers, I'm putting in code snippets in Python, and Houdini can understand that and do here, I'm just doing basic math. If you want to read in data, you probably wouldn't want to do that with a code snippet, but you could still do that within Houdini using Houdini's Python source editor and Python shell. So here you can write a much longer code. Houdini also has source editors and shells for HScript, which is an internal programming language, but I recommend Python since you can use that outside of Houdini as well. So let's talk about an internal format to Houdini that you'll often want to convert your data into if you're doing scripting, and that is a GEO or GEO file. There's also a BGEO, but BGEO is a binary format, whereas GEO is a text-based format, so it's easier to look at and debug when you're looking at the text. So this is an example of a very simple GEO file that describes a very small volume. Let's go through it line by line so we can understand what's happening. This is a header. Doesn't do anything, but you need that in every file. Here, you define the number of points and number of primitives in your file. So we have 1 point because we need to define the center point of our volume. And we have 1 primitive, meaning 1 volume in this file. A primitive can refer to things other than volumes, but let's not worry about that. We have no groups. You can group points and primitives. Let's not worry about that either. And we don't have any attributes. Sometimes this is actually a thing that you do want to pay attention to. If you have, let's say, points, a point can have attributes like density and temperature and weight and all sorts of different types of things associated with it that you would put inside one of these attributes. But in this example, we don't have any. Here we define our center point. So x, y, and z are 0. And the last value is a scale, which you'll often want to be 1. Now here we define our volume. There's a lot of numbers here, but I'm going to point out just a few of the important ones. These 3 numbers define the x, y, and z resolution of your volume. So this will be a 2 by 2 by 2 grid. These numbers are a transformation matrix. Oftentimes it's easier to do transformations within the Houdini interface rather than in this data file, so you'll often want this to be the identity matrix, which doesn't do anything to the data. And all of these other values, I recommend that you just leave them as they are here. I've never really changed them to anything else, but if you want to get fancy, you can read all about what these do and modify them. These descriptions come in a file called gpd.txt with every download of Houdini. And now here we have the data. Oftentimes this will be a very long portion of this file, but in this case we have a very small, simple volume, so we have 8 numbers. And the reason we get 8 is because earlier we defined that this is a 2 by 2 by 2 volume, and 2 times 2 times 2 equals 8, so those numbers need to match up. And finally, you just need to close out the file with these lines. So let's take a look at this in Houdini. Here is my .geo file that I've read into a file node. And if I rotate it around, you can get a better sense for what it looks like. Since my values were alternating 0s and 1s, this is exactly what we would expect to see. So our values were 0, 1, 0, 1. So all see-through on this side and all opaque on the other side. Good, so we confirmed that that works. So now that we've done a simple toy example, we can start working on a real data example. We will be converting a tornado dataset from its native format into a Houdini.geo format so that we can read it into Houdini and eventually create a rendering that might look like this. Okay. Hello, so I think we are live now. Thank you, pre-recorded Kalina. This is live Kalina. So I'm going to share my screen and we're going to start working some more with Houdini. So open up a brand new instance of Houdini if you still have the old example open. We're going to start building up a scene from scratch now, starting with data processing. So the other thing you'll want to pull up is in your downloads folder. There is a code folder that actually has the script that I'm going to be writing live. There's a .py version and a .txt version. They're identical. I just wasn't sure if everyone has a code editor, knows how to use Python, so this txt version might just be easier to open for those that aren't as familiar with it. I'll also want you to take a note of the location within the datasets file of the tornadodata.gda file. If you have trouble finding it in your own file system, if it's not in your downloads folder, there's some hints in our tutorial tips channel on the Discord. But what you might want to do if you're not comfortable following along with me coding, or just want to copy and paste this code, you can do that. Control A and Control C, and I'll tell you where to paste it in. But otherwise, I'm going to kind of type this up live and do a little live demo. So if you have Houdini open, you'll want to go into the Window menu option and go to the Python source editor. So this script that I'm going to be writing is something that doesn't necessarily have to be done inside of Houdini. You could very well run it as an external script. But I'm going to do it in here just so that we all have access to the same tools and know that it should work the same for everyone. So once you open this up, you'll get these two windows. Here's where you type in your code in the top part, and in the bottom is where you'll get outputs. So if you copied and pasted the code, you can simply paste that into here, which I'm not going to do. But so what we're going to do is read in that tornado data file and write out a GEO file that Houdini can read. So one difference between writing a script within Houdini versus externally is that you do need to always define a function. Normally, you might just do something where you just start typing code right away, like hello world. If you're doing an external script, Houdini wouldn't really know when or how to run this. So you really have to put everything into a function. So I'm going to create a read tornado one. And I'm going to just point it at the data file path within my downloads folder. So I know that mine is under my name and downloads. The last part of this should be the same for everyone, unless you change the structure for whatever reason. So here's our file path. Now we want to open our file. This is a file that we want to read, so we use the R keyword and B because it's a binary file, so that's just how you do that. And next we want to define where we're going to be writing our output file. And I'm going to actually write it into the same place, just with a new extension, so I will copy and paste this. Now it's a GEO file. We want to open that file as well. Out file path. And we'll be writing this file, so we put a W for write. Now, the next thing that we need to define is the resolution of our volume. Let's say that this is something that I know because I have been the one that created this data file, or I worked with a scientist. Sometimes, if you just find a data set online, you might not know the exact resolution, and there are different types of tools that you can use to kind of inspect a data set if you don't have this information. And it'll really vary depending on the data format that you're working with. So I recommend that you look up what the file extension is and say it's a .NET-CDF file. You can see that if you were to Google that, you could find that there's a suite of command line tools for NetCDF. I think ncdump is the one that you can type in. That'll tell you a bunch of information about the file, like the resolution. And that'll be different for each data format that you're working with, but this is something that you'll just need to find out. So just another thing that I want to define is I know that in this file, each number is represented in 4 bytes. So that'll just kind of make reading easier if I define this. So the next thing we want to do is to write that header information that we just learned about in the .geo format. And because this is going to actually be identical to what I just showed you in the example, I don't want to type it out. So I'm just going to copy and paste it from the code that I provided, just that little bit. One little annoying thing about the source editor is that sometimes it just appears over the top of everything and you can't really get it out of the way. So you have to move things around to make that work. So let's see, we did that. I'm just going to copy this, just that part to define the header. And like I said, this is exactly the same as what you just saw in the description. 1 point, 1 primitive, no groups, no attributes, center point at 0. The one difference here is that I'm writing the resolution. So if you're not familiar with the syntax, this is replaced by these values here. So I'm setting the resolution of the volume to X, Y, and Z. And here, if you recall, this was the identity matrix. And here I'm also setting that to the resolution of X, Y, and Z. So in this example, I'm actually scaling up the data. Here is where you might also, translate or rotate your data if you wanted to, but I'm going to leave that up to AJ to do inside the Houdini interface instead of doing it in the code in this part. So now is really where the, actually before I get into that, just a little bit more about this header and kind of syntax. I mentioned that there is a file gpd.txt that comes with every download of Houdini. Where that actually gets downloaded will be different depending on if you are on a Mac or on Windows or on Linux. For me, it's a file that just exists in this long area. And if you see in here, I can open gpd.txt. And theoretically that should, oh, it's probably behind, yes, it was behind my editor. So that's just a really long text file that kind of describes all of the different, and some binary at the end. Maybe that part's not important, but all of the different types of data that you can write into a GEO or BGEO file. So this describes both the ASCII form, the .geo, as well as the binary form. You probably wouldn't want to read this file just, from top to bottom, but if you look at just the headers or know what type of data you want to write out, say if you want points, you can just look at this area, or if you want to write a polygon, you can do a Control F for polygon and see what sort of information you need in that header and how to define and describe that file. So this is really, this really has all the information that you'll need to know about creating a GEO or BGEO data format. So, so now that we have this header definition, the next thing that we want to do is to actually write out our data. And this is a really simple, toy example where we are just reading it from a binary file and writing it into a text file. We're not really doing any fancy transformations or translations. So I'm just going to be looping through every voxel in one and writing it out into the other. If you were working with a data format that was, say, spherical or a stretched grid or something that required some kind of conversion, this is where you would do that. Houdini requires that all volumes are uniform Cartesian grids. So you're always going to need to resample or do whatever it takes to get it into that method. But in this simple example, we are just going to read and write basically exactly as it is. So reading in the 4 bytes per number, and then unpacking it since it is in a binary form. And this is just a little syntactical thing. Wait, sorry, I was getting ahead of myself. I'm looking at my notes, but went to the wrong line. So now we've, oh, sorry, one thing I forgot. I'm using this struct library here, but that's not something that, I have by default. So I'm going to go up to the top and import it just like you would if you're writing an external file. You can import anything that you have installed or that, you have access to. So now we can write our value. And actually, I realize now that I wrote this incorrectly. That's what we want there. Okay. Now we're done looping through our data, and all we need to do is close out the file with those last 2 lines. Begin extra and extra. And actually, we need a couple of new line characters in here so that it's all not smushed together into one line. So that it should be our entire simple little script. Once we have that written in, we can click the apply button. And if I had any mistakes or errors that it could detect at this point, they would pop up here. And I don't, so let's put one in here, type in gibberish. If I were to click apply, Oh, interesting. Maybe, I don't know why I didn't recognize that. Let's try a different type of error. There we go. Okay, so now I have a syntax error. This is not a valid value. It tells you what line it is, what the code is, so you can see that that's where you need to fix it. So I'll fix that and click apply. And then we can click accept to close this out. And then we want to go back into the window menu and now open up the Python shell. That's where we can run the code from our Python source editor. And actually, you could have both open side by side. Maybe I closed it too early in case I need to go back and edit it. You can you know, just look at it as you run it as well. But what you want to do in the Python shell to now run this code is we want to call our read tornado function that we defined. And the way that you do that is, since this is defined within this Houdini session, you say who.session, and you can see as I start typing things, it's putting in suggestions. Once I type in who.session dot, you can see that the read tornado is showing up as an option of what you can do in here. So let's run that. And it shouldn't take more than a few seconds. Depending on your computer, it might be slower or faster, but it seems to be working. And once this completes, what we'd expect it to do is to write out this tornado data.geo file in this path. So now we can see that it's finished because these have printed out. So I'll close both of these to get them out of the way. If we go back into the tab menu here, we can drop down a geometry. So you can just press the tab key and start typing geometry, and this will pop up and put that down. You'll see that nothing has happened, which is fine because there's nothing in it yet, but you need to double click on the geometry to step inside, and then we can drop down a file node. So use the tab key again and start typing file. Then you can select that and put it down. And by default, Houdini reads in this default.bgeo, which creates this cube here. We don't want that. So what we're going to do is click this file chooser button on the side and start to navigate to where we wrote out our file. So in my case, it was in the downloads folder, back in the IEEE VIS Houdini folder, and tornadodata.geo. There it is. If you are not seeing this file for whatever reason, or if your code didn't work, or if you got lost, we are providing you with a tornado data final.geo, which should be the same. So if you don't have this one, go with the final one that we pre-made for you. But I'm going to open the one that I just made. So after a couple seconds, you see that the box has disappeared, and we're not seeing a tornado though. So what is happening? The reason for that is because we scaled the tornado way up, so we need to recenter it in our view. And we could simply zoom out and use our mouse controls like AJ has told us, but a neat little trick that you can also do that is sometimes faster and easier is to just put your mouse over the viewport window and then press the G key on your keyboard. And that will just center the view on whatever it is that you have created. So here we can see that we have this tornado, and it's you can see by looking at the numbers down here on the base grid that it's about the size that we expected it to be, you know, in the few hundreds. And this tornado is actually on its side. So I scaled it, but I did not translate or rotate it, saying that, you know, I would leave that as an exercise for AJ. So this is what this data set looks like once we have gotten it into Houdini. So now I wonder if AJ is back, because he will show you next how to actually create a rendering out of this. AJ, are you here? Maybe while we are waiting on him to rejoin, perhaps he's still having technical difficulties, we can open up the next file that we are going to work with, and that's tornadorender.hipnc. So that'll start from this data set that we read in. And we can discard this one. Aha, and that should show you a final scene that we can walk through step by step to see what it'll take to get the tornado to look like this. So I'm going to pause again and check on AJ. He has confirmed he does have Houdini working on him again. But perhaps while we wait, I can start walking through the file after all. Apologies for the technical difficulties. In our team, AJ is typically the one that sets up the scene design. I'm one of the programmers in the group, so I do a lot of the data processing. So he is the better one to describe this to you, but I'm capable certainly as well. So this is the tornado data final geo file that I mentioned came with the file. And you can see that it's on its side, just like the one that we had loaded in previously. To rotate it and get it into the correct position, AJ has dropped down a transform node and connected the input of the file node into that. And all that he's doing is rotating it by -90 degrees. If you're not sure which direction to rotate it into, you could just try all of them. Oh.
Yeah, sorry, we've been madly trying to make licenses work, but so Kalina, I have no idea where you are, but I am back up and running.
Oh, wonderful. So I just finished loading in the tornado data set, and since you weren't here, I opened up the final tornado render scene file and got as far as rotating the tornado. So you haven't missed much.
Oh, good. Oh, perfect. Okay. Well then, I will attempt to pick it up from there. Share screen. Okay, are you seeing my monitor?
Yes. One note though is I started from your pre-made file. So if you want to start from scratch, maybe we should give everyone a moment to close that out and open up a new one. Apologies for the confusion.
No, thank you for vamping for me. So yeah, I think just philosophically, I think it's helpful for people to watch me try to put things together on my own and make my own mistakes, because there are good lessons in how do I fix things that I've broken. So I'm going to start from an empty scene and build it up, starting with the data set that you guys all created with Kalina. So hopefully while I'm babbling here, you guys are either deciding that you're not going to follow along with me or pulling up an empty scene file so that we can get started together. So to get started, I'm going to read in the data. That's obviously a good starting place. So I'm going to use the tab menu, and I'm just going to type file. This is going to create a file geometry container, and inside of it, if I double click, you'll see that the file node is already there waiting for me. So I don't have to, ordinarily you could create a geometry container and then drop a file node inside of it, but this time we don't have to do that. So that's great. So so once I have the file node, I'm going to go over to the geometry file and open up the file browser. And I'm going to navigate to my downloads folder where I have IEEE VIS, go into datasets and choose the tornado data final.geo. And it's a little bit large, so it's going to take a little bit of time to load, but there it is. And so now if I zoom out with the right mouse button, I can see my data there. So I think Kalina got you to the point of noticing that the
viewport is sort of oriented to the XZ plane, but the tornado data set is perpendicular to that. It's going kind of in the YX plane, the XY plane. So there's a couple ways to fix that. One thing that we sort of alluded to earlier is that if you go into Edit, Preferences, General User Interface. Oh, there we go. Sorry, 3D viewports. I think this used to be in the top one, and now it's moved. You can change the orientation of your scene from Y up to Z up, because these are two sort of standard computer graphics orientations. And you'll see that the little gnomon in the bottom left of my viewport, that XYZ little widget, has now changed with Z being up instead of Y, and because of that, the tornado has also rotated. So that's one thing you can do. I'm gonna go ahead and switch it back though to Y up and do what Kalina was suggesting, which is just changing the data. And the way that you do that is with the transform node. So using the tab menu, I'll type transform and drop that down, and I will wire it in, and I will visualize it so that we will see our updates. And then I'm going to rotate by -90 in the X component. You know, if I didn't really know what I was doing, I could do 90 this way and be like, oh, that's not right. And I could do 90 in the Z and be like, oh, now it's just facing me. So a lot of times it's faster to just do trial by error instead of actually like looking up what the coordinates are by doing the math in your head. I'm fully an advocate for trial and error. So we're trying to create a cinematic scene here, right? So a tornado floating in empty space does not make a cinematic scene. So something that will make it feel a little bit more like the real world is if we give it a ground plane. And so to do that, I'm just going to go drop dead simple and create a grid object. Remember, this is Houdini's word for plane, a plane. And so I'm going to use the tab menu, type grid. Again, remember, we're creating a container for a grid. This is just a shortcut to creating the container and the thing inside it. And so if I dive inside, you'll see the actual grid geometry node inside there. When I did this, you didn't really notice a big change, and that's because the grid is way tiny down in here. And so that's not going to do us any favors. And so what we need to do in order to make this a really useful ground plane is change the size. So I'm going to go up to the grid nodes size parameter and just go like 1000 to 1000. And so that's gonna, oh, actually, you know what? That's still not quite big enough. I really want it to go off the edge of the camera. So I think 10,000 is maybe good. You can actually see at the top of the viewport, there's sort of this blue area where that grid just sort of gets chopped off. And that's because the clipping plane of the camera is not very far. So as we discussed earlier, hover over the viewport and the D key will give you this display options, and you go to the view tab, neither clip plane, and I'm gonna make the far clip plane actually a bit larger so that I don't get that clipping, so I can see the edge of my geometry. So let's imagine that 10,000 by 10,000 is gonna be enough for anything we're gonna do. You know, ordinarily you might actually go even bigger than that, but for the purposes of keeping things sort of visually coherent, I'm just going to leave it like that. So the next thing we notice is that the tornado is sort of being intersected by the plane, and we really want the plane to be at the base of the tornado. And so there's a few ways that you can fix this. And I think, let's see, what way do I normally advocate for? None of them. Yeah, okay. So so I guess what I'm going to suggest,
There's actually a script you can write that finds like the size of the bounding box of the tornado, but I don't know that off the top of my head. So I'm just going to eyeball this. And instead of moving the tornado again, I'm actually just going to move the ground plane beneath the tornado. So again, I'm going to use the tab menu to drop down a transform node. I'm going to connect it. I'm going to visualize it. And then I'm just going to translate in the negative y direction until I think that the plane is at the right height. So this is a little confusing because the scene's construction grid is visible and it's sort of mixing with our ground plane. So to hide that, I'm going to go up to the top right of the viewport, and there's this little construction plane icon, and I'm going to click that to get rid of the construction plane. So you can see I can toggle that construction plane on and off this way. So now I'm only looking at my ground plane grid. It's still not super correct. And so what I'm going to do is I'm going to go to an orthographic side view to get it about as close as I can visually. And so the keyboard shortcut for that is space 2. Oh, that's the top. Space 3 is a front view. This is another opportunity to point out, sometimes you just end up floating in space and you have no idea what you're looking at. The keyboard shortcut that always saves me is Shift H. If you hit Shift H, that should center the data that you're working with, except for now, all of a sudden. Perhaps my clipping planes are hiding things? They are. You can see it way off there in the distance. Okay, so part of the problem here, I think, is that I'm centering it on the grid, which is enormous, and I could probably serve myself a little bit better by centering it on the tornado. So what I'm doing here is I'm selecting the tornado, and I'm hitting Shift H, and that's centering the tornado for me. Okay, so now I'm going to go back to the grid. Now I'm going to go back to transforming the grid. And how do I see the grid? Because it is infinitely thin. Maybe the side view thing isn't actually going to work. I feel like normally when I try this, it works. Well, let's see. If we go to like a wireframe mode, maybe things will be obvious. Ha! There we go. So here, this is me doing real-time problem solving. So hopefully there are some lessons to be learned here. So I just changed the viewing of the geometry to wireframe mode, whereas we were in smooth shaded before. If we do smooth wire shaded, we get a nice view of the tornado, but not of the plane. So anyway, sometimes I just click around the viewport until something happens that I want to happen, like now. And so now I'm going to transform that grid down just to the perfect bottom of the tornado, which I can actually do really easily in this wireframe mode because I can see exactly where those two match up.
Question, AJ.
Oh, sure.
How did you drag around those numbers in the translation?
Oh, this is another great thing. Oh, yeah, good point, good point. I can't believe I forgot to mention this. So another thing that I love about Houdini is that when you're sort of doing something that's more of a visual, it's not as useful to just sort of plug in a number and then check it, and then plug in a number and check it. And so they've got these sliders which you can bring up by just holding down your middle mouse button over any parameter. And it'll bring up this sort of number bar, and you can choose sort of how dramatically you want to change your value by moving the mouse up and down. And then let's say I want to go by 0.1. And then to change the actual value, you drag left to right. So you can see it's moving very smoothly here in the sort of 0.1 range. But if I went to 1, it moves a lot faster because it's changing the value by ones instead of by tenths. So yeah, you can do this in pretty much any parameter window in Houdini. Sometimes you'll be in a scale where it doesn't really make sense, but or you might be working with really big data, and so dragging things around interactively is just going to lock up your computer. So I wouldn't recommend doing it in those situations, but especially for something like this, it's like perfect. I think this is actually something that Blender has started doing as well. But when I moved to Houdini, it was the thing that only Houdini did, and it was very exciting. Okay, so I'm going to go back to the perspective view, which is the shortcut is spacebar 1. The other thing that I meant to point out is that these two menus in the top right of the viewport, like they're the only things really inside the viewport, allow you to choose these preset views. The left menu is sort of a bunch of like interactive window presets, and the right view is more focused on cameras that you're using for your scene. So I'm just gonna go back to the perspective viewport by clicking front, set view, and going to perspective. And again, so one other thing about this Shift H sort of centering command is that it doesn't only help you see things that have wandered off your viewport, but if you're tumbling, like you can see right now when I tumble, I'm not really tumbling around a meaningful position. Things just sort of fly by the camera, and I really want to be centered on that tornado. And so when you hit Shift H, which I'm going to do on the tornado, not on the grid, you'll see that it actually centers the the center of rotation of the scene as well. And so that's also a super useful way to kind of get your bearings, especially when you're dealing with really enormous data sets or really tiny data sets. And I'm also going to go back to smooth wire shaded. No, I'm just going to go back to smooth shaded. Oh, okay. No, I'm going to go to smooth wire shaded and just, I think that Houdini 18.5 might have some different viewing defaults that I'm used to. I'm not used to having this sort of wireframe around it. I guess I will get rid of the wireframe. So I'll go back to smooth shaded. Okay. So we've got our data, we've got our ground plane. Let's actually start talking about making a real rendered image out of this. So we've been talking almost exclusively about this OBJ context, which is where all of our sort of geometric assets go. But in order to actually render an image to file, we need to set up a render node as well. So I'm going to go to the out context, and you can see right now that it's empty. Typically, the networks in the out context are not complicated at all. They're like generally just single nodes. And so what I'm going to do is I'm going to drop down one of those single nodes. It's the Mantra node. Mantra is the native built-in renderer that comes packaged with Houdini. If I actually backspace and start typing RenderMan, I guess that's been updated too. I'm not super up to date with what has changed from Houdini 18 to 18.5. There seem to be a lot of things. But if you're interested in using other renderers, you should be able to find the other rendering nodes here as well in the render menu. So I guess what had been RenderMan is now being called USD render. But I'm going to use Mantra. We really like Mantra. Mantra is a really great volume renderer. A lot of the data that we work with is volumetric, and so Mantra is competitive with all the other stuff out there. I've heard sort of in the industry, like, you want a really good polygon renderer, you want to go with RenderMan. If you want a really good volume renderer, Mantra is second to none. Then there's like GPU rendering, which is a whole other thing.
but Mantra comes with Houdini. It's a really effective renderer, and so I recommend it at least as an option, if not the only option. So you can see in the parameter view for this Mantra node is basically any information you would ever want about putting together a rendered image. You can set the name of the output file here. This default name is sort of constructed from a bunch of macros that say, like, in the current scene file directory, create a new directory called render, and then give it the name of the scene file, and then put dot, and then give it the name of the operator. So in this case, Mantra 1, and then give it the name of the frame number, with $F4 is the frame number padded to 4 digits. And then obviously the file extension type, so an EXR image here. In rendering, this is where all of your sort of settings about sampling and how the scene gets diced up and how things get sort of made more or less efficient and more or less speckly happens. This is also where you get to choose which engine is running. Typically, I just use it at ray tracing. You also can enable depth of field and motion blur. For anyone who isn't super accustomed to doing cinematic rendering, motion blur and depth of field have always sort of been talked about as like the two things that really make it look less like, I mean, these days video games look great, but back when they started saying this, they were like, this is what makes it look less like a video game and more like a movie. What makes it look more like it was captured in a camera. But I'm gonna leave those disabled for now, just to sort of save on render time. So the objects tab, this is where you actually tell Houdini what scene assets you want to render. There's sort of this little symbolic language that it uses. So this asterisk here basically means everything. Another symbol that's meaningful is the exclamation point, and that means nothing. There's a little caret icon that means not this thing. So when it says star by default in candidate objects, what it's saying is I'm going to render anything with a blue flag in the object network. So if I go back to the object network really quick, you'll see that right now I've got file 1 and grid 1 blue flagged, and so both of those are going to render. But if I took the blue flag off of grid 1, then only file 1 counts as a candidate object, and so that's the only thing that'll render. Okay, so now if I go back to out and go back to that objects tab, force objects means regardless of the visibility flag, regardless of that blue flag, render that object. So if I moved the star here, it would mean render everything in the scene regardless of whether it has a blue flag on or not. If you want to be specific about which objects you're rendering, this little menu, or the little icon to the right of the field gives you a menu that you can click around in, and so you can sort of click which nodes you want, shift click, accept the pattern, and then it'll actually write the names of the objects instead. And so now if I write grid 1, file 1 in candidate objects, it'll render them both if they're visible, if they're both blue flagged. If I cut those out of there and paste them into force objects, now it will render both of those regardless of if either of them have their blue flag on. They'll both render. And this is typically the format that I like working in. I think that candidate objects can get a little confusing because you kind of forget what you flagged and what you haven't. Whereas when I come to this specific view, I can see exactly what I'm rendering and what I'm not. And sometimes if I really just want to see what the tornado is looking like and the grid is getting in the way, I'll use that caret symbol. And so you actually see when you highlight that view, the caret symbol makes grid 1 red now. And what that means is it's not going to render grid 1. So now it's just going to render file 1, but I still have the name grid 1 there. So if I want to play with grid 1 again, I can take away the caret and now I can see it again. So that's kind of the main stuff. There's some more high level stuff in scripts and driver if you're interested in investigating. The other thing that a scene absolutely needs to have in order to render is a camera view. Now, by default, Houdini, I think, will use the scene view as camera 1 if you haven't created a camera yet. But for the sake of argument, let's actually create a camera and then use that in our render. So in order to create a camera, I'm going to kind of try to get a nice high top-down view of this tornado, maybe from like here-ish. And then I want this view that I've just made in the viewport to become a real camera. And so in order to do that, I'm going to go up to these shelf tools up here. And there's one called Lights and Cameras. And I'm going to hold down the Control key before I click anything. And then I'm going to click on Camera. And what that does by holding the Control key down is it actually assigns the current view to the camera instead of just creating a camera at the origin of the scene. So I find that this is a much more intuitive way to design a camera than to like drop a camera at the origin and then translate it in the X and translate it in the Y and sort of watch it update. So you'll notice that I have this like camera manipulation tool here right now. You can use that to kind of move things around. You can see that I have to drag it pretty far to get any movement at all. I find it pretty confusing and not that useful. So I'm just going to actually, to get out of this manipulate mode, hit the escape key. And so now you can see that tool goes away. So I can go back to just moving my camera around freely. But when I do so, you can see that those sort of gray bars at the top and bottom go away. And if you're looking at the parameter view of the camera up here, you'll see that the camera is not moving even as I move the viewport. And the reason for that is that I've kind of left the camera behind. You can actually see it here. I was basically in the camera view, but the moment I started tumbling, I left the camera view. So what if I want to actually update the camera by tumbling and like using the viewport tools? So I can go and return to the camera just by clicking this no cam and going to restore cam 1. So that'll put me back where I left the camera. And then this little lock icon will tell me to keep like attached to the camera as I move. And so now as I move, you'll see that the values in the camera parameters are updating, and B, the gray bars at the top and bottom of the viewport stay there. And what those gray bars are doing is sort of showing you the aspect ratio of the camera. So yeah, so let's say that I'm like happy with that camera. You can see that the camera has also been dropped down in the network view now as an object. I'm actually going to name it to AJ Cam, just so it doesn't have the name Cam 1. And then I'm going to go back to our render operator, the mantra 1 node. Oh, and you can see, so this is another thing Houdini will do. The camera field is already pointing at AJ Cam. That's because when I created the camera, it had the name Cam 1, which is the default value for this camera parameter. And so when I changed the name from Cam 1 to AJ Cam, this camera field recognized that and updated the name of the camera. So I could change this to Cam 1 and it would be back to pointing to not a real camera, which I assume is going to be the viewport camera. But I'm going to go with AJ Cam because I put all this effort into creating my own camera and gosh, I want to see it. Okay, so now let's make an image. So there's a dozen different ways to do this in Houdini. When you really get into like doing big stuff, you're probably just going to want to throw the job off to like a render farm or a compute cluster. But while you're troubleshooting, there's a couple of things you can do. In the mantra node, you can see render to disk. And that'll just save a file. You're not going to get any feedback from that, like any visual feedback from that. So we're going to skip that. There's this render to mplay, which will open up a sort of sub application of Houdini. It'll be like a new window and it'll show you the image rendering there. typically, I don't find mplay as useful as this third option, which I'm going to show you, which is the render view tab over above the scene view. So if I click on that render view tab, right now we're looking at a black field, but you can see that there's this little render button there. You can see that there's a drop down that says mantra 1. That's the name of the out node that we've been working on. Just for the sake of argument, if I drop down a second mantra node, you will see that now there are 2 mantra nodes in this drop down. So we'll go with mantra 1. You'll see that it's pointing to the ROP camera. That's the render operator camera. That means that it's going to use the camera that is defined in the mantra node. You can override that by using this drop down and pointing at other cameras in the scene. Right now we've only got 1 camera, but be careful if you change this, because you might suddenly start seeing things from a different viewing angle than you expect, and it can be really confusing. That's what's going on. If you just leave it at ROP camera, it will continue to use the camera in the mantra node. And without further ado, I'll click render, and we'll wait a little bit and see what happens. I'm getting a warning I am not familiar with. Hopefully this isn't the thing everyone's seeing. I might be in sort of a weird environment right now because of the aforementioned technical difficulties. So if you have a warning that is confusing you, Houdini will offer you a lot of warnings that are sometimes not actually scene breaking. So understanding what is a problem and not can sometimes be a little confusing. Clearly, I'm getting the image I expect to get, so I'm just going to ignore this warning. You can navigate the render view in a similar way to the way you navigate the 3D view. Middle mouse button pans, right mouse button zooms, left mouse button doesn't do anything here. I think Shift H again will center the image. I think H without the shift shows you the image at its native resolution. So if you want to know like how much detail you're getting per pixel, that's a good way to do that. If you want to figure out what a specific pixel value is giving you, you can right click on the image and use this inspect option. And that'll give you this little floating window that'll tell you all the details about the pixels in your image. What else? Oh, there's a couple hidden toolbars that I'll show you. There's this guy over here. You have to use this teeny tiny little triangle underneath the render button in order to get this toolbar to show up. And this will show you your different image layers. Right now, there's just color. There's a toolbar down here as well, which has a few things. So you can look at the red channel, the green channel, the blue channel. It's black and white right now, so they're all the same. You can increase the exposure or decrease it. You can change the gamma of the image. So that's, and to reset it, you can just click the icon next to it. Same with that brightness. If you just click the icon next to it, that sets it back to the default. This is all stuff that's just sort of good to know when you're fussing around with your render. Another thing to know is the A and C keys are shortcuts for alpha and color. So if I hit A, you'll see now I'm just seeing the alpha channel of the image I'm creating, which is all white, which means that the whole thing is fully opaque. But actually, I'm going to go back to the scene view. I've still got my lock on my camera. So I'm going to rotate the camera so that I'm getting some of the background now. So I'm hoping that that background area is now going to show up as transparent in the render view. And lo and behold, it does. So you can see sort of the translucency of the volume, and you can see the opacity of the ground plane, and you can see the total transparency of the sky, because there is no sky geometry in this scene.
Kalina, can I get a time check? How am I doing on our sort of timeline?
You have 45 more minutes.
Okay, great. Am I more or less on track with what we said for the agenda?
I believe so.
Okay, let me know if I'm forgetting anything, or if anyone's asking questions in the Discord that might direct me in an important direction. Okay, so we are currently seeing a scene with no official material attributes and no official lighting, which, as you may know, are very important features of the real world. When we capture imagery in a camera, we're looking at things with textures, and we're looking at things that are receiving photons that are bouncing from the sun or bouncing from light bulbs. And so Houdini has so graciously included defaults here, so you can see something when you click render. But you know, we want to be really deliberate about what we're rendering, and so we're going to create textures and lights. So, there is one other thing I meant to point out though. Houdini has a progressive renderer. You know what? I'm going to get to that later. I will say Houdini has a progressive renderer here in the render view. So as you update things in the scene, the renderer will automatically update. There's this little recycling icon that toggles that feature on and off. So if you know, if you're dealing with really big data and everything's slowing down, I would turn that off and then just click the render button when you're ready to generate a new image. But you know, if you're working with sort of lighter data sets and you're trying to adjust color or something, it can be a really easy way to quickly get some feedback. Okay, so why don't we start with some textures? So I'm going to go to the material palette here. So this is another tab above the network view. And this is sort of just a place where you can grab some pre-made materials. Generally, in the Advanced Visualization Lab, we're creating shaders from scratch. But when you're getting started, I think grabbing some of these sort of pre-made materials helps a lot to just sort of understand what's going on. So I'm going to scroll down to these volume materials and just grab the billowy smoke pre-made material, and I'm just going to drag it over here onto the material palette. And now you'll see there's sort of this tiger stripe billowy smoke material that I can select, and you can see the parameters up above. If I go back to the network view, you'll see that it's automatically taken me to the material context, and I also have the network here. And if I double click on that, I can dive inside. You can see that it's constructed from nodes, just like any shader would be. Some of this stuff is a little bit more complex than necessary, maybe because they're trying to give you as many options as possible in the pre-made shader. I'll point out that interesting. Again, like things go many layers deep. But if you were trying to create a new shader from scratch, you can kind of use this as a guide. The sort of key here is that this volume model is what's taking all of your math and turning it into instructions for the ray tracer. But we don't have to deal with that right now because, again, all of these attributes have been promoted up to the top level of this network. And so I can just sort of poke around here and look at these pre-made values for the for a volume shader. So let's say I'm gonna change the smoke color to red just to make sure that the shader is working. And you can see that nothing's changed, and that's perhaps obviously a problem because I haven't connected the material to the data set. So in order to do that, I'm going to go back to the object. I'm going to find the tornado, which
I'm actually going to update the name from file1 to tornado just so that I'm more clear about what it is. And that has actually triggered an update in the render because I've changed something in the scene. And then I'm going to go up to the parameter view and go to the render tab of the tornado object. And there's this material field. And if I click on the little icon over here, go into the material network, I'll find billowy smoke. You can also just memorize the name billowy smoke and type /mat/billowy smoke. You're just typing a directory location essentially. And voila, now we have a red tornado. Because remember, we made the color of the density red. So now I want to go back to the material. And to do that, I can either go back to the material context here, or another little handy thing is there's just this little arrow that says jump to operator. And so I'm just going to jump straight there. This is another shortcut that just kind of helps you save 2 seconds when you're dealing with a lot of details. It can help you to just sort of know what's going on. So this data set currently only has a density field. You might be working with a stellar data set where all of the volumetrics have density and temperature and metallicity and any number of other attributes. And so that's kind of what this temperature drop down is for. So typically when you're shading a solid object, you can make it receive light or you can make it emit light, and the same is true for volume. So this is the part where it's actually emitting light. But since it's a tornado, tornadoes don't really generate their own light. So I'm going to get rid of that emission because I don't think that it's actually helping. I think that we just want diffuse material only. But I do feel like the diffuse material right now is pretty thin. Like I shouldn't be able to see the entire horizon behind it. So I'm going to go to the smoke density field and just dial that up a little bit to be a little bit more opaque. And I think that gives us a little bit more of a sense of shape than the translucent look was giving us. I'm also going to go ahead and switch back to a white cloud. I think tornadoes don't typically have too much color in their material, maybe a little bit of like dirty brown. But I'll just go with a sort of white tornado here. You can see a lot of nice details there already. So okay, so now we've got a texture on our tornado. Let's go back to the material palette and just grab a basic diffuse material for the ground plane. And so then if I go back to the material context here, we can click on diffuse. I'm going to say that the color should be sort of a gray brown look. Again, we got to go back to the object context to actually assign that material. And once that's applied, voila, you can see that the ground plane now has a color taken from that diffuse material. These little arrows here in the network view are also super handy for navigating around from context to context. Basically, this will just take you to the directory you were last in. So you'll see, like, if I dive inside the billowy smoke material, I can hit the back arrow and that'll take me back to the material context. So it's not going from context to context necessarily, it's just going from directory to directory, just like a file browser would. Okay, so the next thing that is super, super, super important for any kind of cinematic render setup is lighting. Lighting is really helpful for sculpting complex shapes, especially complex shapes. We often talk about sort of this push to make all visualization 2D. And the reason for that is to remove complexity, right? The idea is that you're trying to simplify your data to only the most important features. But as I mentioned in the earlier video, you miss out on sort of the intuitive experiential sort of aspects of learning about your data set when you're not in 3D. But that doesn't mean that we want things to be as chaotic and imperceptible as the real world. And so lighting is a really great way to sort of draw out details and make things really pop. So if anyone's familiar with cinematic lighting, there tends to be this idea of like 3-point lighting, and those 3 lights that like every cinematic scene should have are the key light, which is sort of your front light that's lighting up the front of your object. There's the rim light, which is sort of a light behind the object that sort of you hope to sort of just get like a little bit of a rim, a little bit of an edge lit up. Typically this is the primary use case of 3-point lighting is like lighting a human subject in full frame in the camera. And so the rim light sort of highlights the edge of their face. The key light lights up the front of their face. And then the diffuse light is the light that sort of comes in from the side and just helps sort of make the rest of them visible. And so those 3 different lights really help sculpt a person and give them some depth and character. That's not always possible when you're dealing with abstract objects as your key characters. You might do a full 360-degree swoop around your data set. And so does the key light travel with you? Is the key light motivated by a particular natural feature? We're looking at a tornado, so the sun is a light. Clouds sort of reflect sunlight, and so they act as sort of a diffuser. So you kind of need to balance like what is the sort of academic theory of lighting with what is sort of makes naturalistic sense in your scene. A lot of times we'll make decisions about lighting that are not sort of based in reality, but they help communicate the data in the way that we really want to communicate. So this is, more fuel on the fire of like, is what we're looking at ever real? Everything that we do deliberately, but whether we're doing it to make it realistic or whether we're doing it to make it communicative is sort of a balancing act. So for the tornado, I'm going to go ahead and so first of all, I'm going to click this little stop icon up here next to the render button in the render view. And that's going to just stop that progressive renderer completely. So that will just save me some time as I'm creating stuff. It won't sort of lag while it's trying to update the render. I'm also going to go back to the scene view and unlock this lock icon. So I don't want to move the camera. I like where the camera is, but I do need to sort of tumble around to decide where I'm going to put the light. So I've sort of lost the camera, but I kind of want the light to be based on where the camera is. So I'm going to highlight the camera, go to view, and then change the icon scale to something a little bit bigger, maybe 20. So now I can see where the camera is, and that'll help me sort of decide where to put a key light. So I'm going to do a key light over here, I think. And again, just like with the camera, I'm going to create the light in the position of the viewport camera where I'm looking right now. And so I'm going to go back up to the shelf tools, and I'm just going to create a point light by holding down the control key and left clicking on the point light. And now we're actually looking through the light. And this is a sort of fun way to change where a light's position is. I'm going to again hit the escape key, hit the lock button, and now as I move around, you can see that the light is moving with me. And you can actually watch as I move how the light affects that volumetric data set. If you look in the parameter view, you can see that the exposure is automatically set to a pretty big number. Whereas if you just sort of created a point light at the origin, that exposure would be set to 1. what this 20 number is doing is it's basically using realistic exponential light fall off and then pumping up the exposure of that light so that it's illuminating the objects in the scene from the distance it is from the origin. So this is sort of automatically trying to create as physically real of light as possible. And so let's just go to the render view and render that light now. Okay. Oh, wow. So like you're already seeing a ton more detail, right? Another thing to point out of the progressive render, if I left mouse button on a certain area of the image and just hold down my left mouse button, you can see that it actually resolves the sampling in that area faster. So, you know, maybe I don't care so much about like this bit here at the edge. And so I'm focusing more on where I'm seeing details and trying to see sort of the interplay of the light and the shadows. But you can kind of compare this back and forth with what it used to be and what it is with the light, and it's night and day. I mean, pun intended. But also, it's just it's so much more beautiful to look at. Just FYI, what I'm doing right now, I really quickly, sneakily, before the second render started, I clicked this little camera icon down at the bottom of the render view. And that stored an image of the last render to this little snap gallery here. And so if I click it again, now you'll see I've advanced to snap 3. Now there are 2 images and the current render in the snap gallery. And so you can see that the second image and the current render image are the same. Yeah, so this is like a really good way to sort of check as you change things, what sort of relative differences you're achieving. So then I'm going to add another light into the scene. So I'm going to stop that automatic progressive renderer again. I'm going to go back to the scene view. So now I want to create a. I'm also going to I'm going to unlock that lock icon and leave the light. And I'm going to create an environmental light. So this sort of behaves as both a diffuse light and a backlight. But it's something that's much more like realistic lighting in a sort of natural environment with the sun and some clouds. So we're basically right now, this key light is sort of behaving like the sun, and we're going to use an environment light as sort of a representation of the diffuse bounce light that comes through the clouds. And so to do that, this time I am just going to create it right in the viewport. So I'm going to use the tab menu I'm going to create it right in the network view. And I'm going to use the tab menu to create an environment light. I'm just going to type env and then hit enter and then click it into the view. You can see that the icon for an environment light is slightly different from that of a point light. And that's because of the way that they're calculated. They have a lot of different parameters that go into them. Quickly backtracking, the point light, you can also change to a bunch of other kinds of lights. For those of you who are familiar with 3D graphics tools, this is like where you would create an area light. A geometry light is a fun sort of recent addition. I guess it's not that recent anymore, but basically that's where you turn any piece of geometry into its own light source. But for now, I'm just going to use it as a point light. It's a little bit more efficient in the renderer, really not by a lot, but just for the sake of argument, we'll leave it as a point light. A sunlight actually should be like either a distant or an actual sunlight. There are different parameters that come with both of those in Houdini. So again, exercise to the reader. Feel free to play with those. Those would technically be more appropriate for representing the sun. So back to the environment light. So an environment light is basically a light that is generated from an image. So it's basically like a skylight. It's sometimes called a dome light, sometimes called a skybox. Well, a skybox is just for sort of seeing the sky. but this is actually using that skybox as a light source itself. And so the most important thing you need with an environment light is the actual image that's driving that light. And so that goes in this environment map field here. And I'm going to fill that in by clicking on the file browser. And then I'm actually going to go to just a default Houdini directory where they have a few environment lights you can use. I didn't create anything in particular for this. But you know, if you were trying to do something really magnificent, you might go out online searching for just the perfect environment map, or you might even create your own. So if I just click over here in one of the pre-created macro-driven directories is this $HFS/Houdini/pic/textures. And then if you scroll, oh no. Is it possible that the new version of Houdini does not have it? Is it an HDRI? Oh, maybe this is new. Oh, cool. Well, everyone's learning with me right now. So it looks like this HDRI directory has some environment maps. So what if we use this Chiara one? Huh, fascinating. I've literally never seen this before. How exciting. So yeah, so you can see that it's sort of this spherical image. If I don't get the grid in the way, you can sort of see that there's going to be this sort of darker blue light coming from the top. There's going to be sort of a tan light reflecting from the mountains around, and I guess even these green bushes, and sort of a lighter blue from the sides. So yeah, so that should sort of just work right out of the box. So I'm going to go back to the render view, and I've already saved this image, and I'm going to click render again and just see what the look changes to. Kalina, I've already forgotten what our timing is like. Can you let me know again?
Yes, sorry, I couldn't find my window. We have 23 more minutes.
Okay, so at 30, got it. Okay, so now you can see there's sort of some colors being picked up on the white cloud from that sort of bluish sky or environment map, which is pretty cool. You can see that the render has slowed down a lot. It's taking longer to resolve all these sort of speckly areas. You can also see that it's sort of blowing out. It's quite bright. And so I'm not sure that I like how bright this diffuse environment light is, but luckily I've got a light intensity attribute still visible right next to the render view. And so I'm just going to take this and go with like a 0.5 on the environment light. So, okay, so now you can see we're getting a little bit more of a naturalistic look. That's pretty nice. There's another thing that's sort of troubling about this image, which is that there's no sky. You would never do this for a final render, but just sort of as a shortcut to getting a better idea of what the sky is going to look like behind the tornado, I'm actually going to go and click this render light geometry checkbox in the environment light parameters, and that's actually going to render the environment light behind us. So yeah, there's these mountains weren't in my old environment light, and so they're sort of having a weird minimizing effect. I wonder what happens if I go with one of these other skies. Yeah, so you're kind of getting this interesting tinyification of the tornado here. So one thing that they always tell you when you're trying to make something look large in computer graphics, or even with a real physical handheld camera, is you want to have that camera at sort of the height of the human eye, which means we are way too high up. You know, we're like flying in the stratosphere in a research jet, and we want to get to like human height. So I'm going to go back to our camera. I'm actually going to disable the skylight and the viewport because it's a little confusing to look at. Okay, so now I'm going to click the lock and I'm going to get the camera like lower down. My high CPU usage is affecting the meeting. Okay, that's probably fine. Okay, so now I'm going to get really low because this is going to feel a lot more like I'm on the ground, like a human is. And now if we look at the render, okay, now we're a little too close, so we can't really see what's going on. Maybe something like that. How do we feel about that? Yeah, that's nice. That's pretty good. There's a definite sort of cognitive mismatch between this environment light and the storminess. Okay, that's indoors. All right. I think maybe the next time I run this workshop, I'm going to need to bring my own skylight. I'm not sure any of these are really making a ton of sense with a dark and stormy tornado. So anyway, this is sort of just a quick look at like how lighting helps you out a lot. I think that maybe this volume is not as dense as I want it to be either. I'm seeing a lot of the background behind it. So I'm going to go in and change that density maybe to 20. And now, yeah, now you're getting some really nice sculpting. That I think I like that a lot better. So yeah, so this is just sort of kind of a high level overview of how to use lights to kind of help sculpt your data set. So I think that's kind of the main stuff that I wanted to go through in the tornado rendering example. I actually plowed through that a lot faster than I thought I was going to. I guess this is something that typically we get a lot of questions in the middle of. So I don't know how the Discord has been going, but since I'm sort of ahead of schedule, this might also be an opportunity to bounce back to that third demo that I ran out of time for in the first half.
I do have a question, actually.
Sure.
Is there a way to inspect the values of this tornado data set like we saw before with the points?
Oh, fun fact, that's actually what we didn't do in the third demo. So maybe that's the next thing to try. Are there any other questions about like rendering stuff before we do that?
No, there have been questions, but Stuart and I have been on top of them in the Discord.
Okay, great. Cool. Well then, I will stop this to save myself some CPU, but I'll actually just drag this out of the way in case any questions come up again. Let's see, I will attempt a little bit of terminal magic to make sure that this opens with the right license. There we go. Okay, so now I'm going to go open that demo 3. And demo 3 is actually great. Demo 3 is all about a Galaxy data set that was given to us by a researcher at the Supercomputing Center named Nathan Goldbaum. Home, downloads, IEEE VIS, Galaxy demo. So Nathan is an astrophysics researcher, and his goal was basically to create a sort of virtual microscope or telescope that reproduced a galaxy much like the Milky Way. For those of you who are not in astronomy, it's very difficult to study the Milky Way because we are sort of smack dab in the middle of it, and so you can't get a sort of top-down view
without waiting billions of years for something to leave the planet and then look back at it. So using a supercomputer, Dr. Goldbaum was able to create this volumetric data set of a galaxy. And this is actually a sort of a stripped down version of an actual scene that we worked on. So we're doing like the real thing now. This isn't just sort of examples of what Houdini can do, but examples of what we use Houdini to do. Which I guess was also the case with the tornado, but I'm sticking to the script as if this came before. So this volume data network is where we bring in all of the volume data from Dr. Goldbaum. So I'm going to dive inside there. Fair warning: the data sets here are downsampled from their original size, but they're still a little bit large. So you may have you may have a little bit of lag as the files open. Don't panic; that's supposed to happen. And if I zoom in, you can even see there's a note here in the file that if you are having trouble loading things and interacting with them, you can stop anything from updating. Like if you just want to change your network without things updating live, there's this little auto update button down in the bottom right of the user interface. And if you switch to manual, that'll just stop anything from updating. And then you can switch it back to auto update when you're ready to actually see things update in the viewport. I think my computer is able to handle this, so I'm not going to do that. But so anyway, you can see these 3 file nodes are reading in VDB volumes that were created externally, I assume by Kalina. I'm pretty sure Kalina did this. These all came from Dr. Goldbaum's data set. They're all sort of co-located volumes that describe different features of the galaxy. There's density, temperature, and metallicity. Each of these have different sort of meanings in terms of visuals. Density tends to describe opacity. Temperature tends to describe emissivity, so like the light being generated by the volume. Metallicity is fully opaque. I think actually density is H2 density. So metallicity and density are actually both a version of density, but metallicity is like anything bigger than hydrogen, and density is hydrogen. This is just like an astronomical convention. And so what this network is doing is it's reading in those volumes, it's renaming each of those volumes. So when the volume is read in by the file node, it just has a name of 0, which if I look at that information, you can see there's just a little thing here that says 0, and then it gives you the resolution of the volume, which is 1024 by 1024 by 100. Which adds up to 104 million voxels. Each voxel is 1 unit in length and height and width. And but the name of the volume is 0, which isn't super useful when you're sort of juggling multiple volumes. And so the density volume now, if I middle mouse button, I don't know if I mentioned earlier, if you middle mouse button, you get that info window, or if you hover and go to that little eye icon, you get that window. And so yeah, if you pull up that information, now you'll see there's a volume called density. Exit out of that. If I middle mouse on name 2, you'll see that there's a volume called temperature. And so then when everything gets merged together further down here and I middle mouse, you'll see that there are 3 volumes that aren't all called 0. So we can now identify them independently. So answering the question that Kalina brought up, how do you analyze a volumetric data set? This volume slice node is a really handy little tool. So it'll basically put a plane through the middle of your volume and assign the values of the volume to the
the points on the plane. The plane will have the same 2D resolution as 2 dimensions of the 3D volume. Now I'm not looking at the volume, so I should Shift H, and there we go. Now we're actually centered on that slice plane. So a few things to know about the slice plane. It sort of by default looks in the XY plane, but you can also do a YZ slice. So you can see it's a very skinny galaxy. You can do a ZX slice. But clearly XY makes the most sense in this context. There's also an offset, so you can sort of slide the plane from side to side in the volume. Excuse me. So it's kind of a big data set, so it's a little bit laggy, but you can see that the sort of color of the data is updating as the plane goes back and forth through the data set. I'm going to switch that back to 0. And perhaps most usefully, if I middle mouse on the plane that has been created, you can now see all of the attributes that this volume slice node are creating on the plane, which include things like color, position, and temperature. And so if I go back to this geometry spreadsheet above the scene view, you will now see the values of your volume being sampled at that location. So I can now quickly see within this slice where the minimum temperature is and where the maximum temperature is. Oh, I'm like, why is it calling it temperature? It's because I've told it to call it temperature in this attribute field. So really, this should be called density, because that's the name of the volume. And that's also the default name of a volume slice if you drop it down. If you don't like the sort of rainbow color of the view, you can also go grayscale or something else for the look of this. If you're trying to narrow in on a specific range of values, you can change that range and get some things that are a little bit more meaningful. This is especially useful if you're dealing with a data set that, or with a data field that goes from like 0 to 1 million. Whereas this density field is sort of within the 0 to 1 range pretty comfortably. So let's see. Let's talk more about modifying stuff. So I'm going to skip that purple box for a second, and I'm going to look at changing volume values. So notice this is just coming out of the density volume. So we're only looking at the density volume at this point. I just hit the blue visualize flag on the sort of the end of the density network. And so you can see that we're looking at the sort of 3D volume representation in the viewport. For me, this doesn't do a lot in the viewport, but it's at least sort of gives you an idea of the general shape of the volume. And both of these two little stacks here are here to sort of show you different ways that you can manipulate volumes as geometry in the Houdini network. So the first one is a volume VOP. We talked a lot about attribute VOPs when we were looking at that Antarctica digital elevation map. So you can that was manipulating points. That was a point attribute VOP. But now this is a volume VOP, so it's pretty similar. The sort of pre-existing nodes that you get with the volume VOP look similar. The global inputs are very similar. The output is only a density field, because most volumes, I guess, are just thought of in terms of sort of a collected amount of semi-opaque particulate. And then I've just dropped in a logarithm node here, and basically this is just going to run, instead of running over every point in a sort of mesh, it's going to run over every voxel in the volume. and just apply the same function to it. And so in this case, we're doing a logarithm base 10. I'm going to see if I change this number, if I can get the viewport to kind of update a different look for the volume. But maybe not. It's not looking too different. Am I? Oh, I'm not actually looking at it. Okay, so I'm gonna visualize it. There we go. And then dive back inside. There we go. So if I go back to 10. Oh, I guess it's sort of still invisible. If I click this bypass flag, this is a good sort of use case for the bypass flag. You can see what it looks like without the logarithm and then with the logarithm. And then I have another volume slice node here. And so we're going to look at what it's actually done to the values, because again, the viewport is not a great accurate representation of what your render is going to look like. So it's always good to sort of actually monitor what values you're getting. And so you can see now if I bypass that volume VOP, the galaxy looks one way. And when I don't bypass it, it looks a different way. So clearly we are modifying the values. We can also talk about sort of scripting with actual text. So if I highlight this volume wrangle, a wrangle is basically just a node where you can write VEX code. And VEX is sort of a C-style language. So I'm going to use C-style comments to get rid of the first part of this. And create an error. Oh, right, because I don't need an else. If I'm not doing an if. Okay. So you can see that here now I'm multiplying the density by 1.5. I can also multiply the density by a really small number. Okay. Control Enter, by the way, is how you actually execute the code. Enter just is a return line. You can also just click out of the text box and it'll update. But yeah, so now you can see if I take the density way down, it sort of shaves off a lot of the surrounding density and only shows you the really dense inner part of the galaxy. So the stuff that I commented out is just sort of to show you that you can also do voxel trimming based on position. So here we're saying any voxel where the X value is greater than 600, set the density to 0, right? So that just sort of slices our volume off. Typically, you wouldn't slice right through a data set, but you might do something to like get rid of a weird edge, for instance, if there's like an artifact near the edge of a data set or something. And once again, you can see in this volume slice that the values are in fact being updated. Sort of just more proof to my statement. So we're quickly running out of time. So I hopefully this scene is sort of explaining the answer to the question that Kalina asks. Just a lightning fast overview of what the rest of the scene looks like. We're using a Houdini table import node to read in a point cloud from a sort of a CSV file. It's actually a .chan, but it's organized in a similar way to a CSV. Just white space separated columns, and that reads in stars. And then we use the stars and the volume together in the final render. This H2 container is using an object merge node to bring in something that's going to get one shader, and then the gas and dust is bringing in geometry from a different part of the network to apply a different shader. And then we've got an out node called Galaxy Render that's already set up. And so if I just click render in the render view, hopefully in these last few seconds, we will see what the scene actually generates. and I highly encourage you to click around this scene to see if you understand how it works, how the shaders for the volumes were put together. And of course, if you have any questions, always feel free to reach out to us after the fact. So I think with that, I'm good with the demos. Kalina, do we have anything else, or do we just want to say goodnight?
I think that's everything. If anyone has follow-up questions, feel free to post them in the Discord even after the session, and we'll try to get to them. So thanks very much for joining us today.
And I do want to throw out another plug for Houdinis. If anyone's interested in looking into Houdinis, let's see, am I sharing my desktop? There we go. Houdinis.org.com. It's not an organization. So this is a great piece of middleware that Kalina has put a bunch of time into creating. Oh Lord, who knows what's going on with this computer? But it's I'll stop my screen share. If Kalina wants to share it, she can share it. But this is something that several people here at the NCSA have put a lot of time into. It is a great way to connect scientific software with cinematic software and get some really beautiful results of really complex data sets. And also a good way to track down our contact information if you have further questions.
And the website does actually appear to be down, so you'll fix that immediately.
Oops. So yeah, without further ado, thank you everyone for attending. Sorry for the little bit of a rough start, and have a great rest of IEEE VIS.
Thanks. Bye.
Thanks.
Taylor-Coyer flows is a turbulent fluid motion created in the gap between the two rotating cylinders. The traditional reason-based methods are only able to capture the small-scale coherent structure. The detection of the large structure depends on the 2D cross-section, which is not the true configuration. We adapt the feature-level set methods and the density estimation to combine multiple attributes and use them as the filter to separate large and small-scale structure.
Confusion flow is an interactive visualization for the performance analysis of classification models. It introduces a novel temporal adaptation of the confusion matrix, which lets model developers compare the learning behavior of multiple classifiers over time. Find out more about confusion flow in our talk or in our TVCG paper.
How do you visualize the nanoscale, 1/1000th of a meter, for the public? As part of a Science Center exhibition, we developed an immersive environment that explains nanoconcepts by allowing users to explore nanoproperties. We reflect on how exploration, the confluence of explanatory and exploratory visualization, can be applied to visualization in public spaces.
Digital humanities present great opportunities for testing new visualization approaches and evaluation techniques. However, and given the diffuse character and novelty of the field, it may also be intimidating for novel and senior researchers willing to get started in the discipline. In this paper, we propose a data-driven analysis of visualization for the digital humanities to identify key themes, authors, and relevant publications. So if you want to know more, please read our paper.
A testing environment for continuous color maps. Many other fields in the computer science do it, we should do it too. With our work, we introduce the approach of using test functions as a standard evaluation method. We present a test suite for continuous color maps implemented in the CCC tool. Adapt the task to your requirements at the interactive testing section and observe them at the testing evaluation section.
In our current work, we visually compare two cohorts of segmented and classified tissue images, originated from single-cell omics data. To that end, we developed data-driven and interactive workflow implemented in a multi-linked view system. Finally, we show the effectiveness of our workflow through specific case studies.
Scatter plots and parallel coordinates are widely used for visualizing multivariate discrete data. However, for multivariate continuous data, the continuous scatter plots and continuous parallel coordinates are more suitable. In this work, we extend them to uncertain data. Additionally, we also extend fibers to uncertain data. If you are interested, come to our presentation.
We present the first generic design space and library for visual piling. Inspired by physically piling paper documents, visual piling describes an interface for spatial organization of visual artifacts into piles of partially overlapping items. Piling affords interactive grouping, arrangement, previewing, browsing, and aggregation to reduce the complexity and support comparison of large collections of small multiples.
Deep neural networks are vulnerable to maliciously generated adversarial examples. This brings high risk in applying these networks to safety-critical applications. We develop a visual analytics approach to explain the root cause of such wrong predictions. Our contribution contains a constrained path extraction method, a river-based visualization, and a contribution analysis method.
CMED is a visual analytics framework for exploring medical image data annotations acquired from crowdsourcing. CMED can be used to visualize, classify, and filter crowdsourced clinical data based on a number of different metrics such as detection rate, logged events, and clustering of the annotations. CMED provides several interactive linked visualization components to analyze the crowd annotation results for a particular video and the associated workers.
Several recent studies advocated the use of non-parametric density models for the improved characterization of data uncertainty. The non-parametric models, however, present the challenges such as increased memory and computational requirements. In this work, we propose an efficient non-parametric framework for volume rendering in the context of uncertain data and show their effectiveness in classifications via comparisons with the other statistical models. Morse complexes have shown a great utility in understanding the topology of complex scientific datasets. The noise in the scalar field, however, can significantly distort the Morse complex topology. Hence, we study the extraction of Morse complexes for ensembles of noisy scalar fields through their uncertainty visualization using our proposed statistical summary maps.
Asteroids have always been and will always be a threat to life on Earth. Most likely, an asteroid will hit deep water, but what properties will actually lead to a threat like a tsunami? Ensemble simulations are a common tool to understand the effect of different parameters like the size of the asteroid. We propose an interactive visual approach to help analyzing deepwater asteroid impact simulation ensembles.
We present TransVis, a design study that is proposed to analyze and integrate close and distant reading of multiple translations. TransVis presents the overview of the collection to capture global patterns that is facilitated by the ADM-VIF matrix. TransVis integrates a detailed view to explore interesting path of alignments. We also propose the TLC view to examine and explore the terms of the user-selected path to justify and reason the AD analysis.
We have seen many visualizations for tree data structures, but when showing changes in trees over time, some focus on displaying hierarchy, while others highlight their changes. With split streams, we combine two approaches and their individual benefits. We evaluated our method in a user study and consider it a general-purpose method for the visualization of dynamic hierarchies. Our JavaScript library is openly available.
In this study, we designed a system named Causality Explorer to facilitate the causal analysis. Users can explore the causal graph to perceive the causality and its uncertainty, validate the causality with the raw data, and apply the confirmed causality to what-if analysis.
We asked participants to recreate bar graphs. When the bar was alone, we saw a different pattern of error than when the bar was presented with context in a stacked bar graph. We find that absolute error increased for higher bars when they were presented alone. We also found that there was a bias in the responses such that they were repulsed from an implicit 50% mark. We found a magic number, 10%, to predict error. Participants are usually within 10% of the height of the bar.